Hello, Professor Limaco. How are you? Okay, Professor Colting, are you there?
I am, yeah.
Okay, so let's try to share your slides again.
Yeah.
Excellent. So let's wait just a couple of minutes.
Yeah.
Okay. So it's my great pleasure to introduce our first speaker today. Is Professor Tobias Kolding from MIT. So thank you very much, Professor Kolding, for accepting our invitation. Professor Kolding will talk about geometry of partial differential equations. So please go ahead.
Great. Yeah, thanks so much for the opportunity to speak here. Yeah, so I want to talk about geometry of PDEs, and I'll try to give you a flavor for from a large and very active subject by talking about some particular examples. So optimal geometry and evolution of shapes are governed by PDEs. The geometric invariance makes the PDE canonical, and it means that the same type of equations appear over and over again across many diverse areas. The equations also describe phenomena that are unrelated to geometry, and this is part of that they are very natural. Often understanding the geometry of the equation unlocks the structure, and it leads to fundamental tools in PDE. Understanding the equations require simultaneous insight into both analysis and geometry and the interplay between the two, and I will illustrate this with various examples. And I will emphasize in this talk, I will emphasize some big ideas and themes. I will suppress many other interesting aspects and results, but hopefully it will give you a taste of this large and active area. My talk here will focus on joint work with Bill Minicozzi. So here's the three examples that I want to talk about this interplay between analysis and geometry. I'll talk about it in showing optimal regularity in PDE. I'll talk about it in stability of solutions. And then I will talk about it in the geometry of the diffeomorphism group, or if you will, the geometry of the gauge group. So these are the three examples that we'll discuss. In this first example, in PDE, existence is often proven using weak methods. So this could be distributions, or it could be viscosity, right? So using weak methods, one establish a weak solution. The challenge is then to prove regularity, right? And nonlinear, if you're dealing with, and that's what we will be dealing with here, nonlinear PDEs, then weak solution might not be smooth. And some of the questions that first arises then are how smooth are solutions and how big is a set where the solutions are not smooth. Okay. And so that was the first example. This was the first example. So the first example is this dichotomy between existence and regularity. The second example that I want to discuss is stability of solutions. So in dynamics and PDE, a central question is often which solutions are stable, which are not. The stable ones are the ones that physically happen, and the unstable one are the one that you do not see in nature. And the slides, the four snapshots you see on this picture, that's of a soap film. And so actually the first one is a soap film. So the first one, we'll return to that. The first one is what's called a catenoid. This is where you are revolving the curve hyperbolic cosine around an axis. And it's a piece of that. And that is, we'll talk about that in just a minute. That's a minimal surface. And the snapshot here is that if you take this, it's a highly unstable surface. If you perturb it ever so slightly, then what you see is that it's completely changing and it will not return to itself. Okay, and so we'll return to that in just a little bit. So that was the second. So again, the first of these three examples is existence versus regularity. The second is stability of solution. And the third one is the geometry of the gauge group, or the geometry of the infinite-dimensional diffeomorphism group. And so the geometric properties are universal. They are independent on the coordinates that you choose to look in. So, but in different, if you look at the question in different coordinates, you would see something very different. And so the question then is, how do you recognize a geometric objects when there is no natural coordinates? And so understanding, in this case, understanding the geometry and the PDE that is involved in the diffeomorphism group then becomes a central question. Okay, now where do the equations that I want to look at, where do they come from? So the first one is if you're dealing with surface tension. So surface tension gives a PDE that describes evolution of shape. The mean curvature is the force of surface tension, and surface tension causes water to form roughly spherical droplets. But so the mean curvature again, that is the force of surface tension. So mean curvature, if you take recall that if you take a surface, then the mean curvature is the sum or the average, if you will, of the principal curvatures. And so if the surface, and later on, we will think about the surface as a level set of a function. And so if the surface is given as a level set, then the gradient of the function, that's normal to the level set. And so the unit normal is then the normalized gradient, and we call this a bold n. And the mean curvature, there's a nice formula for the mean curvature. In this case, the mean curvature is just the divergence of the unit normal, so it's the divergence of this normalized gradient. If the right, so again, the surface tension is given by the evolution of mean curvature. We'll talk about that. And when that is the only force that is acting, then equilibrium is when the mean curvature is 0. Those are called minimal surfaces. Minimal surfaces have a long history, go back to in mathematics, go back to 1740 with work of Euler, and later in 1755, the beginning of calculus of variations by Lagrange. And so the surface that you see to the left, that's part of the catenoid. It's a small part of the catenoid. Remember that the catenoid is this where you're evolving hyperbolic cosine around an axis. And that surface it's minimal, the mean curvature is 0, but it's highly unstable. If you take a small enough piece of it, and the picture to the left, that's a small enough piece, then actually it is stable. And you would see that in nature, but you wouldn't see the full catenoid. To the right, you see half of the surface called the helicoid. So the catenoid that was discovered by Euler in his work in 1740, where he realized that was a minimal surface. The picture to your right is half of a double spiral staircase. That's the surface called a helicoid. And so it's half of the helicoid. And that was discovered in 1776 by Mouchet. And it was in his thesis, he was a student of Monge. And the reason why it's half of the helicoid is that half of the helicoid is actually stable, whereas if you take the full helicoid, it's highly unstable, and you wouldn't see the full helicoid in nature, but half of it you can indeed see, and it's realized as in that illustration as a surface spanning a wire, as you know, by a soap solution. Now, the mean curvature flow, that is the evolution or when the only force is surface tension. The only force acting on the surface is surface tension. And so a surface, and this could be in any dimension, the surface is evolves by the mean curvature flow if the time derivative of the position vector, so if at a given point, that point is moving a given point on the surface, the derivative of the movement of that point is minus the mean curvature times the unit normal. Right? And so, so you see in this illustration, if you're looking at it, I don't know if you can see if I'm pointing like this, but this point here, that is so right. So we're thinking about the surface as a boundary of the light blue domain, and so if you're looking at this point here, that's a convex point. For a convex point, it means that the movement will be inwards. If you just check the equation, then it means that the movement here at a convex point will be inwards. And And on the other hand, if you take this point down here, that is a concave, right? So seen from the surface, that is a concave point. And so the movements there will be outward, right? And so you see from this sort of simple illustration, which is of course illustrated, I mean, it could be in any dimension, but it's illustrated as if it was a curve in the plane. Again, it's the boundary of the light blue domain. Then you see that the convex points move inwards and the concave point move outward, right? So everything is kind of shrinking. That seems sort of clear already from this picture. But you also see that it's in some way becoming rounder, right? Because the convex point, they will move inwards, will mean that they will maintain their roundness, whereas the convex point will move outwards, so they will become right. They will become to some extent rounder because you're looking at it from the inside. Okay, so you see from this sort of picture, you see that there's some sort of smoothing going on, right? And so indeed, the mean curvature flow is a heat type equation. It's a nonlinear heat type equation, and it is the negative gradient flow for area. It's a negative gradient flow for area, but it's acting on the infinite dimensional space of surfaces or hypersurfaces, say, in Euclidean space in this case. And so the flow makes the area, so because it is a negative gradient flow, it means that it makes area shrink as fast as possible. Mean curvature flow has been studied in mathematics and also in material science long before material science existed as a separate field, but for more than 100 years. In mathematics, it was studied already in the 19-teens, some version of that. And in material science already in the 1920s, so independently on the work in mathematics. A nice example to keep in mind of evolution is what's called Grayson's dumbbell. So this is the boundary of a dumbbell. This is a surface in our tree. Topologically, it's just, of course, a sphere, two-sphere. But the geometry is not like the standard two-sphere, right? It is like these two barbells and the thing connecting the two barbells. And so the evolution, so these are 6 snapshots of the evolution. And you should look in the top line first from left to right. So in the first picture, you have the surface at the initial time. And what you see is that the neck, right, is quite thin. It's quite thin compared with the bells. And what you see is that the neck, everything actually, because it is a negative gradient flow for area, so everything is shrinking. But the neck has very high mean curvature because of the cross section. The cross section is a relatively small sphere, circle, and so this means that in this circle direction, the principal curvature is large, and so this means that the neck that is joining the two bells that will shrink much faster than the bells. And so within a relatively short span of time, the neck, that's what you see in the third picture, that the neck will pinch off. The two bells will still be sort of relatively nice and round. But because it is a heat type equation, it's nonlinear, and that means that you have this kind of singularity. But it is still a heat type equation, and so it will also have a smoothing effect. So it will have this reaction and diffusion effect where singularities occur, but it will also have a diffusion effect that gives you regularity. So the singularity occur. Once a singularity occurs, the smoothing take over and it will become instantaneously smooth, and then it becomes rounder and rounder, right? So you see that, you know, you get these spikes. The spikes you really, the little cusp you wouldn't really see. I mean, that just happen at the time where the singularity occur, and then it will instantaneously be smooth after that, but with very, very high curvature at the peak. And that high curvature will then go down. But then after a while, but everything, you know, is shrinking to a point. So in general, the curvature will go up, right? And so that's a good example to keep in mind in the discussion that follows. Now, so let me see. So another example to keep in mind is what's called the Merritt ring. The Merritt ring is a thin torus of revolution. And so this is the initial surface. It's a thin torus of revolution. If you're looking at the evolution of this under the mean curvature flow, then it will remain a torus of revolution until it have shrunk so much that the whole surface become extinct in just a circle, just a round circle, right, in a plane. So that's the second example. And so let me just say a couple of words. We'll get back to this later. That the takeaway here in the first example is that it's smooth except at in this case that except at 3 singular times. The first one is when the neck is pinching off, and the second time is where the two bells are disappearing, right? And so if you're thinking about the singular space, the singular set in space-time, then there are these 3 points in space-time where it's singular and it's at 2 different times. And in the second example, the singular sets just happen at 1 time and it's just a round circle. Okay. Now, in many different areas of science and engineering, computer science, in the medical fields, in imaging processing, in computer science, in finance, in all kind of area engineering, then you want to track a moving front. And so this is typically done by what's called the level set method that is extremely widely used, both in applied mathematics and certainly also in computer science and medical engineering, medical imaging as well. In computer science, it's called the snake method or the active counter method. In mathematics, it's called the level set method. And the idea is this: so you want to track the evolving front. And so the idea is that you think about the front. So you want to turn in this geometric object into some PDE, right? So of course you have a PDE on the geometric object, but you will rather look at a PDE that is about a function on Euclidean space. And so the question is, can you do this? And what PDE do you get? And so again, so we're thinking about the front as a level set of a function. And then you want to find a PDE for this function. And so what you do is that you're looking at, so in order to get a PDE for the function, it's not just, you want to not just look at the level set, one particular level set of this function. You want to say that all of the level set of the function is evolving by the same PDE. Okay, that's the idea. And then, you know, so that will give you a PDE. And then you can afterwards, you can then just track, say, the 0 set. But you then get a PDE for a function. Okay, and so you see this is illustrated in this example where you have it could be tracking the counter of forest fire, right. So one of the strengths of this level set method is that it's allowed for singularities and it allows for topological changes, right? And so, right, so this is illustrated, the gray and the top, the bottom part of the picture, that's supposed to illustrate the graph of the function. And the top part of the picture, the gray areas, that the boundary of the gray areas, that is the level, a particular level set of the function. Okay. Now, right, and so this is a big theme actually that in what follows, in at least part of what follows, is that you can think about. I mean, the level set method is a way of that you're looking at the evolution of a front, but you can turn it into a PDE, and then you're looking at the levels. So the evolution of this surface is then about the evolution of the level sets. And so we'll talk more about this in just a bit. So this here is an example that is where the front is, and that's what I will mostly discuss in the next few slides, is where the front is moving monotonically. So by that I mean that if the front is moving in just one direction, and then it will have to move inwards because everything will be shrinking. So if the front is moving monotonically, then you can think about what's called the arrival time function. The arrival time function is the time when the front is arriving at a given point. So if you take a surface in, say, R3, it could be in any dimension, a hypersurface in any dimension, and suppose that this hypersurface is mean convex. Mean convex just means that the mean curvature is positive everywhere. If that's the case, then the front will move monotonically, and it will keep moving inside itself. Right? And actually, as in moving inside itself, it will sweep up, the evolving front will sweep up the entire domain that the initial surface is bounding. Okay, and the arrival time function is then the time when the fronts arrive in a given point. So the arrival time function is defined on the domain that is bounded by the original, the initial surface, right? Because the initial surface under the evolution will sweep up the entire domain that it's bounded. It bounds initially, right? So this gives a function, and again, it's a time when the front arrive, and that's called the arrival time function. And that actually, so here's it's illustrated it's illustrated in the plane where it's a convex curve. If you take a convex curve, then it will just move inside. In higher dimension, you just need mean convexity. It will move inside, and the level sets equation then becomes a PDE, an elliptic PDE. So the arrival time function will then satisfying an elliptic PDE, and this PDE is at the bottom of this slide, and you see that it's degenerate. It's degenerate because it doesn't evolve second derivative in all directions. And it's also nonlinear. That's pretty clear from the equation that is nonlinear in U. And then to make matter even worse is that it's not even defined when the gradient of U is 0, it's not even defined, right? And so remember that this is the arrival time. So in this picture here, right, it's the arrival time. Well, if you're looking at the boundary, that's the initial front. So on the boundary, this is the time when, if you think about it, if you have a point on the boundary of this domain, then that's the time. So any point in the domain that is bounded by the initial boundary is that's where the arrival time function is defined, and it's the time when the front arrives. But at the boundary, it is there at time 0. So the function is constant 0 on the boundary, right? And so, of course, the function must have some, right, and then it becomes positive in the inside. So obviously there's a maximum. So you see that you cannot avoid, I mean, you will always have points where the gradient of the function vanishes, right? Okay, and so that's, so it's this, it's an elliptic, it's a degenerate elliptic nonlinear PDE that's not even defined when the gradient is 0. And we'll get back to how to define that in just a minute. Let's look at a couple of examples that will play an important role later on. So the two examples, two simplest examples, but they actually turn out to be very important. So these are just in R3, just to illustrate it. You could do it also in higher dimension. Everything works in all dimension. And so the first example is where you take a round sphere in R3 again. You're looking at the revolution. If you normalize it, so now I normalized it so that the sphere, so it's not the initial time is not 0, but I normalized it so that the final time is 0. If the final time is 0, then the arrival time function is this quadratic polynomial that you see on the top, x1 squared plus x2 squared plus x3 squared, and then this minus 1/2 in front. That's the arrival time function for the round sphere. If I, as long as I'm normalized so that it becomes extinct at time 0. Time 0 and of course at the origin space. The second example is where you take a round cylinder, and if you take a round cylinder and it becomes extinct at time 0 in the line where x2 and x3 are 0, then it becomes this quadratic polynomial at the bottom of the page. So that's the arrival time function for the round sphere. Okay, so now the arrival time equation that's central in many areas, is central in applied mathematics. And it goes back to Osher and Session. It arises in all kinds of areas, for instance, in game theory. And it fits into a larger family of natural PDEs, nonlinear PDEs. Existence and uniqueness was established in the early 90s by independent work of Evans and Sprook and Chen, Giger, and Godot. And so what they proved is that solutions exist in the viscosity sense, and they're Lipschitz. And so the fundamental question is then, so you have these weak solutions to this second order nonlinear elliptic PDE. You know that the solutions exist, so they actually prove both existence and uniqueness. So solutions exist, they're unique and Lipschitz. And the question then, the fundamental question is then, how smooth are solutions? So it was already known back then in the beginning of the 90s by work of Tom Ilmanen that in general solutions are not C2. Let me just recall for you what it means for a function to satisfy something in the viscosity sense. So, so suppose you take a continuous function you want to be able to say that a continuous function satisfying some elliptic PDE in a viscosity sense. And so I will illustrate this with the Laplace equation. And so we say that a continuous function is subharmonic, or the Laplacian of it is non-negative for x at x equal to 0 in the viscosity sense, if there exists a function b that has the same value as 0 as u, and b is supposed to lie below u. B is assumed to be smooth, and b is has the Laplacian of b at 0 is supposed to be positive or non-negative. If you so this is what it means in the viscosity sense for a function to be subharmonic, or subharmonic just at the point x, but you can then of course define it every, you can say that a function is subharmonic if this holds at every x, and the barrier function b, right, is allowed to depend on x, right? And so if so this here gives you a nice way of talking about that that functions that are not even differentiable are subharmonic, and they are supposed to be continuous, but they're not even not necessarily even differentiable. And if you have that a function is subharmonic in the viscosity sense, then the maximum principle will actually hold, right? And so at the bottom of the page, you see here a simple example of a function that is not even differentiable. It's a function on the line, which is just the absolute value. And it's clear, right, that this function is satisfying that it was smoothed away from the origin. So you just, and it's obviously the Laplacian is 0 away from the origin. And so you just need to check that at the origin. And that's also clear enough, right? That it is, there you can just use the barrier, the constant function, the constant 0 function as a barrier. Anyway, so the key point here is that for functions that are just continuous, you can talk about that they're satisfying some equation in the viscosity sense, and you can, and in particular, you get the maximum principle. And so that's how the solutions to this arrival time function, arrival time equation, just to go back, sorry, to this degenerate PDE. This is what Evans and Spook, Chen, Giga, and Goddard did, that they showed that solution to this degenerate elliptic equation exist, are unique, and are Lipschitz. Right, but they're satisfying the equation just in this viscosity sense. Okay. Now, and so again, the central question is then, that solutions are not C2. This was already known 30 years ago by Tom Ilmanen, but is Lipschitz really the best you can do? And so now, and this is where this interplay between analysis and geometry comes in. And so Bill and we showed that in fact, the arrival time function, it's not just Lipschitz, but it's actually twice differentiable everywhere. It's always twice differentiable everywhere. Again, that solutions are not C2, but in fact, you can also classify, being C2 has a geometric meaning. So you can completely classify when the solution is C2. And so, right, so, and this is this second result with Bill, that the arrival time function is, so again, the arrival time function is always twice differentiable, but it's always twice differentiable, and the second derivative is always bounded. That's what we also proved. I didn't state that, but we also proved that the second derivative is always bounded. But you can actually classify when the arrival time is C2, and it's C2 if and only if the entire evolving front becomes singular at the same time, and then it becomes singular and then extinct, right? At just one time and then extinct, right? And so you see that that's exactly what we saw in the example of the marriage ring. For the marriage ring, the evolving front, it was remaining a thin torus revolution, and it eventually became extinct in a line, right? Not in a line, but in circles, right? In the example of the dumbbell, then the behavior of the evolution was different, right? So there, the neck pinched off first, and then later on the true dumbbell, right? So this means that it doesn't become singular at just one time. And so you see that our theorem here applied to this case, and it will say that it's not actually C2, right? And in this rotational symmetric example, this is actually what Tom checked, is that it's not actually, Tom Illman checked that in this case, it's not C2, right? In the rotational symmetric case, but in fact, right? It's just very general principle that for any surface, the arrival time function is C2 if and only if the entire evolving front becomes singular at just one time, and then afterwards it becomes extinct, right? So these two theorems together, right? It gives you really optimal regularity, right? Optimal regularity for this PDE. Instead of just knowing that the solutions are Lipschitz, then actually they are twice differentiable everywhere. And instead of knowing that they're just satisfying the equation in a weak viscosity sense, then actually what you can prove is now that they satisfy that the solutions are always twice differentiable, and they're always satisfying the equation, not just in a weak sense, but actually in a classical sense. Okay? And then you can even classify when the second derivative is C2. Okay, now I want to talk a little bit about, so how do you prove this result? So in order to explain that, let me just remind you how do you prove that a function is, what does it mean that a function just of a single variable is differentiable, right? So one way of thinking about that a function is differentiable and function on the line is differentiable is that on all small scale, it's supposed to look like a linear function, and that linear function is supposed to be the same. It's supposed to look like the same linear function on all small scales, right? So it's not only is it supposed to look like a linear function on all scales, but as you go even at a smaller scale, it's supposed to look like the same linear function, right? Because that linear function is going to give you the derivative of the function at that point, right? So that's one way of thinking about that, what it means for a function to be differentiable. In the case of, so a sort of famous example where you don't have differentiability is the Koch curve. This is, I think, the first fractal curve. The Koch curve, let me just remind you, the Koch curve is given by an iteration process. That if you take a line, so the top, k equal to 0 at the top, you see that that's the start. So you take a line, you break that line, you divide that line into 3 parts. The middle part, you replace the line between in the middle part, a line segment in the middle part by this angle. And now you have, after you have done that, you have 4 line segments, 1, 2, 3, 4, each of these line segments. Then you do the same process. You divide it into 3 parts. The middle part, you replace the line segment by an angle, right? And so you repeat this process over, right, over and over again. And in the limit, that's when you get a cock curve. And so if you're thinking about this process is, so imagine that this angle that you are replacing the middle third with, it's the same, right? It's the same angle at each time, but it's scaled down. Right? And so imagine that this angle is the angle is close to 180 degrees to pi. If you do that, then it will, what you will see is that if you're looking at it at the cock curve under a microscope, then on any given stretch, you would see something that is close to a line. But as you're going down on a smaller scale, the line, it will also look like a line, almost like a line. But it will look, but if you're looking at different points and at different, if you not just at different points, but at different scales, then you will typically see a different line. And in fact, that line, as you're zooming in, will look like it's rotating around. As you go from one scale to the next, it will have rotated a little bit, and then you go to a further down, it will have rotated even more. Right? And so here you see an example where on each scale, it looks like a line, but the line is not unique. It changes from scale to scale. Right? And so now, I can see already that I won't get to all of these things I want to talk about, but I want to at least try to give you an idea of how to use geometry to prove optimal regularity in this case. And so what we do is that we're looking at, right, so the geometric way of looking at this PDE, the arrival time function, is to look at the level sets and the evolution of the level sets. And the PDE way is, of course, is just to look at the PDE on Euclidean space. And so we want to sort of go back and forth between these two things. And so the flow is so this is sort of classical, that the flow or the function is smooth away from critical point. The critical points, that's where the function is really, very ill-behaved. And so we're looking at a point, so that's where we want to establish that at all of these critical points, we want to establish that the function is twice differentiable. And so what we do is that we're looking at the rescaling of the function. So we define this function b lambda. So the lambda is a positive constant. And so you're looking at the scale b lambda. This is a kind of, you see that this squared, it's just because the equation really comes from something parabolic in a way. Okay, and so you can easily see that this b lambda, this will satisfy the same equation. So if u is an arrival time function, then v will also satisfy the arrival time equation. Okay, and you also see that if you take a homogeneous quadratic polynomial, then this is preserved, right? So if u is a homogeneous quadratic polynomial, then v lambda is, for any lambda, is the same polynomial, right? And so remember that in the two examples we looked at, the two basic examples, the shrinking spheres and shrinking cylinders, the arrival time function in those cases was a quadratic polynomial, right? So it means that in those examples, b lambda is independent of lambda. And so now we want to prove that the function is twice differentiable, and what we need to do is we need to establish it where the equation is badly behaved, and that is where the gradient vanishes. And so we want to prove that it's twice differentiable, which means that we want to prove that there's a second order Taylor expansion, a unique second Taylor expansion. And so what we must show is that in terms of these v lambdas, we must show is that these v lambdas, right, has a limit as lambda goes to 0, right? This is like the rescaling of it, right? And so in general, there's not any reason to expect a limit, even for a subsequence. It was proven, and so it was proven that by work of Briskin, Ilmanen, and White, they showed that you get geometric blowups. So you get for every sequence, you have a subsequence, and that subsequence converge, right? And the blowup is, so in general, the blowup will be solitons. It will be dilation invariant solutions called shrinkers. But the question here is that, so what they proved is that you get this subsequence for a given sequence of rescalings, you get a subsequence that converge. But the question is, again, the fundamental question is, might it be like the Koch curve, where if you take one sequence of rescalings around a point, then you get one blowup. But if you take another rescaling around the same point, you get a different, right? That's what happened in the Koch curve. You get a different blowup, right? And so that's like the fundamental question, right? Do you get a unique limit, or does the limit depend on the sequence of blowups? Okay. And so for monotone flows, these limits has been classified. They were spheres and cylinders. They're spheres and cylinders. But again, the fundamental question is the limits unique or not, right? Is it possible that if you take another sequence of blowups, you would always get these cylinders of spheres? But is it possible that if you take another sequence of blowups, then you get a cylinder with a different axis, right? And that's a big question. And so, Bill and I proved that actually you get uniqueness, that the blowup does not depend on the sequence of rescalings. So, and this kind of questions about uniqueness has a long history in geometry. It's have long been realized as fundamental. This is the most general case actually where it's known. There was fundamental works in the 80s, early 80s by Almgren and Allard and Leon Simon on these kind of uniqueness questions for minimal variety. Now, using this uniqueness, then Bill and I proved that the function U, so this is the solution to the arrival time function, that it always looks like a quadratic polynomial and always like the same quadratic polynomial on all small scales, right? And so this gives you a second order Taylor expansion and proves that the function is twice differentiable. And I will stop here. I didn't get to a bunch of the other stuff, but my time is up. So thanks very much.
Thank you, Professor Kolding, for this very, very clear and interesting talk. So we have enough time for questions. So if someone has a question for Professor Kolding, please go ahead. Just raise your hand and then please unmute yourself. Maybe I would like to start with the questions, Professor. If the same somehow model that you did for the example of the Koch curve, one can also extrapolate, for example, in other settings like Cantor set, characteristic functions of Cantor set of that also have similar fractal structure.
Yeah, I mean, so right, that's right. So now when you ask, let me just say that. So this uniqueness. So I don't know if I can. I just wanted to when you're asking. I don't know if you can see my slides here. I think maybe you can't, but like the uniqueness, this is also related to proving results about the singular set, right? And so you can imagine that this, like the example with the cock curve is an example of a curve that is not rectifiable, right? It doesn't have finite length, right? And so using this result about uniqueness, so remember in the example of the marriage ring, you get that the singular set is just a circle. And so now by very general methods, geometric method theory methods, then Brian White established that say if you have, I mean, again, these things hold in all dimensions, but if you have, if you're looking at this monotone evolving front, and if you in R3, then the singular set is one-dimensional. But this is like, the singular set, right? But what you want to know is just like for the cock curve, you want to know, does it have finite length or not, right? Not just whether the dimension is. And this using, if I had had more time, I would get to that using this uniqueness, you can then prove that the singular set actually has finite length, and you're getting some nice structure, C1 structure on the singular set.
Okay.
Right. So yeah.
And maybe other question is in this in your theorem of classification that the function U is of C2 class. My question is if you can go beyond of 2 orders of regularity, or if one can gain order of regularity beyond of 2, even if one don't has one if and only if result. Is that possible?
I mean, so again, what we prove is that the solution is twice differentiable, and that the second derivative is bounded. There's a uniform bound for the second derivative, and it's known that it's not C2, right? But we can actually classify when it's C2, right? So it's but there's also I mean, there are solutions that are C2 and then not C3. It's a quite delicate thing. Yeah.
Oh, okay, I see. Thank you very much. So are there more questions for Professor Tobias Kolding? Okay. It seems that people was happy with your talk, Professor Kolding.
Okay, great.
Yes, thank you.
Okay, thank you.
Yes, okay, so let us see if there are some comments. Not? Okay, so Professor Kolding, thank you very much for your talk, and thank you for accepting our invitation. You are welcome always to our conference, to our activities in ICMA and Latin America.
Okay, great. Well, thanks so much for the opportunity. Thanks.
There is another question. Don't know.
Okay. Please, Brian, go ahead.
Oh, in the chat.
In the chat. Luis Yapu asked if the result on C2 is specific to the main curvature flow.
Yeah, it is, and that's a good question. And so again, it's related to a lot of other PDEs, and it's still inside larger families. There are, and it's not known in. I mean, it's not known like for this the infinite Laplacian. For instance, this kind of optimal regularity is not known. There's, it's not known for like the P Laplacian. I mean, there's various other equations of this degenerate equation, and this kind of regularity is not known for any of those. But it's like would be super interesting, of course, to know. And I think this is like, I mean, this provides you a general framework, but it's not known in these other settings.
Luis say thanks. So it's very nice to see that our participants are doing very nice questions in the conference. Thank you. Okay. So thank you very much.
Okay, great.
Professor
Okay,
Collin,
thanks
again.
so much. Okay, bye.
Thank you. So I will pass the chairing to Professor Juan Limaco.
Professor Enrique Fernandez Cara, please screen your slide, please.
Good morning. Yeah, I'm going to share the screen.
Not smell.
Is it
Yes.
okay?
Excellent, excellent.
Thank you.
To Munich. To Munich for start.
Yes. Go.
Thank you very much, Professor, for accepting our invitation.
Thanks to you. It's always a pleasure to be invited. So thank you very much.
Well, it's an honor for me to introduce to Professor Enrique Fernandez Cara, who is one of great mathematicians in the area of control theory and partial differential equation today. Professor Fernandez Cara received his doctorate in 1981 in France under the guidance of Roland Growitzky. And currently he has already oriented 13 PhD students and 28 descendants. Likewise, his scientific production is high, having published 230 articles and have approximately 5,000 citations. He is chief professor in the Department of Numerical Analysis and Differential Equation of the University of Seville. And in this occasion, Professor Fernandez Cara will give the talk entitled 3 Results in the Control of Fluids. Welcome, Dr. Fernandez Cara, and you can start.
Okay, thank you very much for your presentation. Thank you very much to the organizers for the invitation to this conference. I'm very honored to be here and to try to present a talk on 3 results on the control of fluid that have been obtained very recently by us. So I'm going to start. Excuse me, I cannot. Okay. I will try to present a brief summary of control results, and then I will try to explain the equations that we are going to to consider. They come from fluid mechanics, and as you will see, lead to some very particular difficulties, both from the theoretical and the numerical viewpoints. More precisely, I will try to present controllability results for this called the Boussinesq system, and then some minimal time control results for the same kind of equations. But let me start, as I have said, with some, excuse me. I cannot go ahead. I have some difficulties here to go ahead. Now, okay. What is control theory? Control theory is this discipline on mathematics in which we try to decide how we can act on a system in the best way, in general, in a good way, or even in the best way. It is a multidisciplinary area involving maths, physics, engineering, etc. And it's strongly motivated by applications, past and recent applications. And among them, we can cite something like the irrigation systems a long time ago in Mesopotamia, the constructions of aqueducts, or more recently, all what is around the steam engine. For example, the question of how can we convert heat into motion has been a strong motivation of control problems. Nowadays, we find control problems in many areas. For example, in biomedicine, in population dynamics, structural mechanics. Control is also present in the construction and the behavior of description of the behavior of autonomous car driving, etc. I like very much an example concerning the models that we have been using for epidemics and pandemics to explain what kind of control problems can be considered, and more precisely to explain the difference between the two most important viewpoints adopted in control theory, whose names are optimal control and controllability. So let us consider this system, that this is a relatively simple ordinary system, formed by 4 variables, Q, S, I, and R, that represent the quantities of quarantine, susceptible, infectious, and recovered individuals in the pandemics. You see that this is a well-known system that has been used not much time ago to describe the behavior of the recent pandemics. This has been completed with an additional equation, the equation for Q, that it is not so standard, in which we make consideration of quarantine people. And there are a lot of coefficients that appear there, and among them we have 2 important coefficients, lambda and rho, that we let depend on T, and that represent the action that we are going to introduce in the system. Lambda and rho determine respectively the quarantine rate and the vaccinating rate in the system. So typical optimal control problem for this system is the following. How can we choose lambda and rho in order to minimize something that we indeed want to be small? That is, the total number of infectious people plus the effort that we are paying, the effort that we are introducing in the system in order to vaccinate the individuals. Of course, a very similar optimal control problem can be formulated here by changing rho by lambda in case in which we pretend to use as a small quarantine strategy as possible. This is an optimal control problem. How can we choose a part of the data of the problem, lambda and rho in this case, in order to minimize something? Okay. Another viewpoint is adopted when we try to choose lambda and rho in order to make the system reach to a particular situation. For example, this is a very interesting problem to choose rho and lambda in order to get I of t, the final number of infectious people, equal to a desired value, ID. Or the same can be asked if we pretend to choose rho and lambda in order to get a very large number of susceptible people as D at the final time, capital T. Well, these are controllability problems. For controllability problems, we try to choose the unknowns that we are allowed to choose, that is the controls. We try to choose them in order to make the system reach a desired state. Okay. Well, this is the difference between optimal control and controllability. And we are trying now to apply these ideas to systems that, in fact, are much more complicated and come from fluid dynamics. More precisely, I will work with the Navier-Stokes equations and also with the Boussinesq system. The Navier-Stokes equation is, as you probably well know, a system where the unknowns are U and P, velocity, field, and pressure, that is assumed to be satisfied by a Newtonian fluid, an incompressible Newtonian fluid. And the Boussinesq system is more or less the same, but it is a much more complicated system because it is coupled to a transport diffusion equation, a kind of heat equation, in which the unknown, the new unknown, is the temperature, zeta, and it is assumed to be valid. It's assumed to model the behavior of a fluid in which heat effects are important. Here, the term zeta times k is a vector, represents a force created by heat. This force has an influence on the motion, and this is the reason by a term that we find on the right-hand side. And at the same time, zeta is influenced by transport, by U, and has to satisfy another equation that it is this one, okay? Control problems are interesting for these kind of systems if we try, for example, to minimize turbulence effects. In that case, we should choose controls, for example, data on the boundary, in order to minimize this quantity. Also, if we pretend to transport fluids from one place to another in an optimal way. Also, if we want to design some objects that have an influence on the motion of the fluid, like parachute, wind tunnel, aircraft, etc. Also, if we want to control the flow of water in some reservoirs, or introducing river deviations, something like this. Also, if we want to control blood flow with the bypass design, etc. So control problems for fluids are very important, and I will try to present now some results, some theoretical and numerical results that, in my opinion, can shed some light to some of these problems. The starting point is going to be a controllability question. Let us consider the Boussinesq system. I remember you that this is the system satisfied by U, P, and zeta, in which we have a motion equation for U and P and a heat equation for zeta. I will try not to write it in order to explain this as clearly as possible. And we have completed the Boussinesq system with some data on the boundary, on the lateral boundary, some data for U and for zeta, but only on a part of the boundary. I mean, I'm going to consider a domain like this one, and I will try to control by fixing the boundary data on U and zeta, only gamma, unless U equal to 0 and zeta equal to 0 on the rest of the boundary, in order to get a system like this. So this is starting at time t equal to 0 from 1 U naught zeta naught, and the controllability question, the null controllability question, is whether or not are we, once U naught and zeta naught are fixed, whether or not are we able to find F and H controls such that at capital T we have U equal to 0 and zeta equal to 0. This is the controllability question. This is called the null controllability question, global null controllability questions, because we have the desire to choose U naught and zeta naught as large as desired, as possible. So this is a global null controllability question for the Boussinesq system, and this is the problem that serves here in this talk as starting point. Okay, this was conjectured for the Navier-Stokes more than 30 years ago by Jacques Louis-Lyons, and there have been a lot of partial results, all of them in the positive direction. So it is assumed, it is expected that the answer is yes, but the conjecture for the moment is open. It is not closed. I'm going to present two results that are in some sense steps towards the completion of the to give a complete answer to the conjecture. The first one is a quasi-global null controllability result, and I will try to explain this now, in a cube. So let us consider the same problem, but this time we are going to consider a domain, three-dimensional domain, like this one. And I'm going to fix U equal to 0 and zeta equal to 0, for example, on this face. And I can control the values of U and zeta on the other 5 faces. So U equal to F and zeta equal to H, with F and H well chosen, are admissible choices for the solution consensus problem. The unique place where I fix equal to 0 the values of U and Z and zeta is this. Well, the result says that if we have this geometrical situation, then once we fix the initial state U naught, zeta naught, there exists a sequence F epsilon, G epsilon of, let us say, ghost right-hand sides, such that first they go to 0 appropriately, and then if we put F epsilon and G epsilon on the right-hand side of the equations, then the problem becomes null controllable. I mean, for each epsilon, we have that we can find boundary data for the solution to this system such that at capital T, we have U equal to 0 and Z and zeta equal to 0. This is the result. F epsilon and G epsilon go to 0, so we have modified a little bit the equations, but not too much. And then we get contours that drive the solution to 0. This is the result. This result is also applicable to more general domains, but for the moment, they have to be domains with a flat piece of boundary. I mean, a domain like the one I'm going to show here, this one is admissible. I fix u equal to 0 and zeta equal to 0 only here, and we work on the boundary data of the rest of the boundary, and then the result is the same. We can get, again, a sequence of epsilon, G epsilon, such that for each epsilon, the system becomes null control. Let me briefly present the main idea of the proof, because I think that this is interesting, and it is probably generalizable to other situations. And this is the idea that I want to present here. How can we do to prove the theorem? How can we do to prove the theorem for a modified equation with epsilon, G epsilon on the right-hand side? We do as following. We fix U naught and Z naught and zeta naught. We fix the initial data. And then we take a time t1 close to the final time, capital T, and do nothing. And for the moment, during the interval 0, t1, we do nothing. We leave the solution evolve alone. That makes a solution that at final t equal to t1, we have some regularity of kind H2. And during this interval, we do nothing. Then, in a second small interval from T1 to T2, we perform some regularization solution. Some regularization at the price of introducing a small ghost on the right-hand side, a small F epsilon, G epsilon on the right-hand side, but keeping the control equal to 0. And the third step, this is the first main step, what we do is to drive the solution to a well-chosen capital U, capital zeta at the third time t equal to t3 in such a way that first we introduce a ghost, a small ghost, we keep the contour equal to 0, the boundary data equal to 0, and overall capital U and capital zeta are chosen in such a way that they solve a much simpler problem that can be controlled to 0. So this is a step in which we make a bridge between the Navier-Stokes equation. We introduce a bridge between the Navier-Stokes equation satisfied by U and zeta and a new system satisfied by capital U, capital zeta. It has a much simpler structure and can be controlled to 0. In fact, capital U and capital zeta is components by components given by this system of equations. We have a heat equation that is alone, and then a 2x2 system of parabolic equations. And it is known that this is a system that can be controlled to 0 from the boundary. So in the final step, which is the second main step, what we do is just this. We introduce a control that is able to drive the solutions phi, psi, and zeta to 0, controlling just on one side of the boundary. This is the situation. Let me explain all this with a figure. This is the situation that I have described. We do nothing during a long interval. We perform a regularization of the solution. And this is the main point. We introduce the right-hand side of the equations that is able to drive the solution to capital U, capital zeta at time t equal to t3, and then we control to 0. In the last subinterval, of course, the right-hand side is 0, and the right-hand side is only different from 0 in these two small intervals. And this is the reason that we are able to take right-hand sides arbitrarily small. Okay? This is the situation, and this is the result, and this is the proof. Okay, some comments. This proof, this kind of proof, was formally developed by Sergio Guerrero, Oleg Imanuilov, and Jean-Pierre Puel for the Navier-Stokes. So this is a generalization to the Businek system. And in this generalization, we have introduced...
¿Quieres tu café?
Sí.
Ya.
¿Todo bien?
Sí, ¿cómo estás?
Bien.
¿Cómo está todo?
We have introduced some variants that make possible to control the final parabolic system. Let me say that there exists a better result by Coron, Marbach, Suer, and Zahn, better in the sense that F epsilon, G epsilon have a good convergence. In fact, what they do allows to have F epsilon, G epsilon that converge in the space that is fixed in abundance. So in some sense it is better, but to my knowledge it is only valuable for the two-dimensional Navier-Stokes equations. So a good task would be to generalize the result to other more general situations. And the main point, the main comment is that at present, we have estimates on the right-hand side, F epsilon and G epsilon, but we don't have known estimates for the boundary contours. That is to say, here we have been led to introduce some right-hand side that depends on epsilon, and we don't know how is the dependence with respect to epsilon of the contour that we have to put on some part of the boundary. If we had some bound here, of course, this would lead to the null controllability of the Businek system. But for the moment, the estimates of the control are unknown. Okay, let me now present a second result. Again, a partial result on the null controllability of the Navier-Stokes equations and the Businek equations. This is a second result in which what we do is to change the boundary conditions. Instead of saying u equal to 0 and zeta equal to 0 here, what we say here is that u times n is equal to 0. That means that the fluid slides, and of course is the normal vector in the boundary. So this says that the fluid slides on the boundary. This equality that says that the tangential efforts originated on the boundary by the fluid are proportional to the tangential velocity. The second condition relating the tangential stresses, tangential efforts of the fluid and the tangential velocity. And an additional well-known condition, Fourier condition or Robin condition, that says that the heat flux is also proportional to the temperature on the boundary. So I have changed the boundary conditions, and then once the boundary conditions have been changed, we are able to say that in that case, we do have global null controllability. I mean, we fix the initial data for u and zeta, and we can find f and h on some part of the boundary such that if we put u equal to f and zeta equal to h on this part of the boundary, then in that case, the solution to this problem, in which I insist that the conditions have been changed on the complementary boundary, on the complement of gamma, the solution to this problem at capital T vanishes. Also, let me say that this theorem is extendable to the concept of global exact controllability to the trajectories. I mean, if I fix a bounded and regular trajectory, U bar, P bar, zeta bar, then the same result can be obtained by changing U equal to 0 at final time by U equal to U bar at final time, and similar inequalities for P and zeta. So this is illustrated in this figure. We start from this point and we do nothing. We don't apply any control. Then the solution probably does as the black curve shows. This is a desired trajectory in which the initial state is a little smaller, and it arrives at final time t equal to 2 at this point. So the result says that we are able, with these new boundary conditions, we are able to find F and H such that, starting from this point, we can follow this kind of bridge between this point and this another point, and we can reach, the solution can reach exactly the final time of the desired trajectory. So this is also true, although it is a little bit more complicated to write and to deduce. This is the sketch of the proof. It is very technical. It is very technical, so I will not go into the details. I'll just explain, in some sense, the main steps that we have to follow in order to prove the result. First, we perform an extension from omega to, we go to a larger set O in such a way that we change the problem from a boundary control problem to a distributed control problem. I mean, instead of asking U and zeta satisfy these conditions, we introduce right-hand sides locally supported in space, right-hand side for the equations, and we fix U equal to 0 and zeta equal to 0 on the whole boundary. This is the idea. Excuse me, not on the whole boundary, on the whole extension of the boundary of gamma. This is the first step. In the first step, we go to our distributed control problem, in which the question is the same. Are we able to find xi, eta, and sigma such that at capital T we have, again, U equal to 0 and zeta equal to 0. Then we perform a change of scale, and with the change of scale, we are able to convert the initial data and the coefficients of the Laplacians of U and zeta, I mean the diffusion coefficient for zeta and the viscosity, we are able to convert all these quantities into small quantities. And at the same time, we take a large time t prime. So the change of scale permits to work with a small initial data, with the small coefficients for the Laplacians, and in a large interval. And then, after the scale has been changed, what we do is to decompose the solution and the right-hand side controls, as this formula shows, in a very particular way, in which one by one the terms are going to be either small or either equal to 0 at a large value of t. This is very technical and very complicated, but believe me, it is possible to do. As an important part of this decomposition is that we have to introduce a boundary term, because in order to get these conditions well satisfied, we have to correct in some sense the decomposition that we have introduced here. And V, that is a part of this decomposition, has to satisfy a Prandtl-like equation near the boundary. Okay, after some work, we are able to choose the controls in such a way that at a great time, at near capital T prime, everything is small. And then, as a final step, what we do is to apply a local result that is able to drive the solution exactly to zero. So this is complicated, as you see, but this is what we can do in order to get the null controllability result. Two questions. First one, is it possible to do the same what we can call the true Boussinesq system? In the Boussinesq system, it is usual to neglect a term on the right-hand side of the heat equation. This is a term that is assumed to be small, and it is neglected very usually. And what I have described until now is the Boussinesq system without this term. So there is an open question here, an interesting open question, which is just to know if whether or not the null controllability problem is also satisfied if we keep this term in the heat equation on the right-hand side. And another question to my knowledge open is whether or not we can do the same kind of things, local or global results, for variable density Navier-Stokes equations or variable density Boussinesq equations. Variable density Navier-Stokes and Boussinesq equations are obtained if we couple these equations with the transport equation for the density. This is a system that has to be satisfied by a fluid in which heat effects are important. This is the reason that we have here a term, and the equations are coupled, again, as before, with the transport diffusion equation for zeta, and the density, the mass density, is variable. And this is the reason that we have to add another variable, rho, that is not constant in general, and an equation for rho that is of the hyperbolic kind. So it is an interesting question. As I have said, I think that it is open, whether or not we can extend the control results to a system like this one. Let me now present a third and final result. This is a result that is obtained for a kind of reformulation of the controllability problem. I will try to present another viewpoint, again, trying to find controls that make the solution reach the desired state. But this time, I'm going to concentrate on the time that we have to use in order to reach this desired state. In other words, for simplicity, I'm going to consider the Navier-Stokes equation, and I'm going to put right-hand side control, a distributed control, located on the small domain, omega, instead of a boundary control as before. This is just for simplicity and in order to avoid some technicalities. And the new problem that, as I have said, can be viewed as a reformulation of the previous one is the following. I fix an initial data, U0, a final data, final desired data, UT, capital T, and I fix also delta, small delta, positive delta, and I try to minimize the time that I need to make the system evolve from U0 to a state, U capital T, close to UT, in the sense that the distance to UT is equal to delta. This is the new reformulation of the problem. Of course, there can be no T. If the controllability problem is not satisfied, if UT is not reachable, there can be no T. But if there is one T, we want the minimal one. This is the problem. Approximate formulation, that is in fact the formulation that we are going to solve, is this one. I introduce this function that depends on capital T and F, which is the control that I'm going to put here, and introduce this function. We have a component related to the largeness of T and another component related to the largeness of F, the size of F, and try to minimize this quantity subject to T and F in appropriate space and U of capital T minus UT with the norm equal to delta. This is an approximate formulation of the previous one, the previous problem, and of course, depending on a constant B that we have put here. And then, if we are able to solve this problem, possibly we will try to do B go to 0 to see what happens. Okay, what have we done for this problem? What have we done in collaboration with Marie Gaite recently for this problem? We have done three things. The first one is that we have proved that if the set of TF for which the admissibility conditions are satisfied is non-empty, what I have called there HAD, which is the admissible set of couples TF. If it is not empty, then there exists a solution to this problem. This is the first thing we have proved. An existent result for this constrained time minimal problem. The second result, which is, in my opinion, the most important, is the following. We have proved that if capital T and F is an optimal couple for this problem, it's a solution to this problem, and U is sufficiently regular near capital T, which is a very reasonable assumption because of the parabolicity of the system, then in that case, we can deduce an optimality system for T and F that identifies the couple. And the third result is really a numerical result. We have found an efficient computation method in order to compute T and F. Let me explain the second one, which is, in my opinion, the most important result. It is this theorem. If TF is optimal, is a solution to the problem, and U is sufficiently regular, in particular near capital T, then in that case, we are able to prove that TF, the associated state UP, and a joint state ZQ that has to be introduced, and a multiplier lambda, satisfy this system in which we find the motion equations. This is nothing but the motion equations, a kind of a joint equation, This is the reason that it is backwards in time for Z and Q, as is usual in optimal control theory. A relationship between the control we have found and the adjoint equation that is of the same kind that we find usually in Pontryagin principle, and then the conditions U at capital T minus UT norm equal to delta, and an additional relation that is including capital T, the multiplier lambda, and the solution associated to T and F. Okay? This is the optimality system that we find. It is written here. In a more schematic way. Navier-Stokes equations, an adjoint system, a Pontryagin relationship between f and z are the equalities that we need in order to assert that we are at the solution of the problem. Okay, the proof that we've found uses the so-called Dubovsky-Milutin formalisms. This is a very interesting principle and elegant principle, I should say, for this kind of problems. And the idea is the following. The idea is that in order to prove the result, we know that there do not exist descent directions for the function that we're minimizing that are at the same time admissible directions for the constraint. So there are some kind of separation between the descent directions for phi and the admissible directions for the constraints. And using duality theorems, this is equivalent to say that non-trivial linear combination of dual directions has to vanish. When we try to write with detail the linear combination of these dual directions, we find just this system. It has to be detailed, but it is not. It is complicated from the computation viewpoint, but it is not so complicated from the conceptual viewpoint to arrive from the linear combination of dual directions to this system, in which, as I have said, we find for the moment three things that remind a little bit optimal control problems, and then two relations that assert that we are in the solution that we are looking for. Okay, the numerical method that we have introduced, is the following. First, for a lot of lambda t, for a lot of pairs lambda t, we compute the solution of this optimal control problem where we have the Navier-Stokes equations, an adjoint system, a related adjoint system, and the Pontryagin characterization of the control. Then, once we know for each lambda and capital T, U, P, Z, Q, and F, once we have computed all this, we try to solve this 2x2 system, where the unknowns are T and lambda. We try to solve this 2x2 system, and then we arrive at the solution to the optimality of a system that is probably a candidate, a firm candidate to be the solution of the minimal time control problem that we have started from. So this gives lambda B and TB, because B is a quantity that I have introduced here and that appears in the problem. This gives lambda B and capital TB. And then natural question is to know what happens as B goes to 0. Okay. Let me show, in order to finish, the numerical solutions that we have found in a simpler model. A simpler model, the numerical results that work for the Navier-Stokes equation and also for other more complicated equations are now in progress, but I can show you some previous numerical results obtained for the heat equation, in the case of the heat equation. So the problem now is to minimize function like the previous one, that is an approximation of this T2/2, subject to the distance from zeta, capital T, minus zeta t equal to delta, and zeta is the solution to the heat equation, a simpler equation in which we can show what happens. This is the domain where we are going to work, the circle, the control region. We are going to apply a control here, F is applied here, and the mesh we have been using in order to get the numerical results. This is the desired state. The desired target. We want to minimize the time needed to get this equality with this zeta t. Zeta t is this function. And we have taken in this experience delta equal to 0.05, and we have started from 0. Okay, now I'm going to show you what we have computed. We have computed first the norms, zeta of capital T minus zeta t, these norms for many values of t and many values of lambda. Mu, that is here, is more or less the reciprocal of lambda. So I have represented mu because it's easier, that mu is 1 over lambda. So we have computed for many values of t, many values of lambda, this norm. Then we have computed for each t the lambda corresponding to the equality zeta of t minus zeta t equal to delta, which was 0.05. So for each t, we have computed the corresponding lambda. In fact, we have represented here mu, which is more or less the reciprocal of lambda, and this gives this curve. So for each t, for each final time, we have a lambda such that this is assured. And then what we have done is to solve the equation t equal to minus lambda this quantity, which was the second equation in the 2x2 system I have to solve. So this is the value, these are the values of t, these are the values of lambda multiplied by this scalar product, and the solution is here. And the solution gives the time t star, which is the minimal time that we need in order to get a distance equal to delta. So this was the desired target. This was the function zeta t that we have fixed at the beginning of the experiment, and this is what they have found. So this is a function that we have computed this way. This is the value of zeta at capital T that behaves similarly to zeta t at a distance equal to delta. Okay. This is a three-dimensional view of the same function that appears to be the function that gives the solution to the problem. Final comments and questions. In the case of the Navier-Stokes conditions, we know that there is a global null controllability result. So in that case, we know that TB, capital TB, goes to 0 as B goes to 0. So the interesting question is whether we are able or not, we are able to deduce this property that we know that is true from the characterization that I have presented. Maybe this could give a help for the Dirichlet case in which we don't know whether or not this property is satisfied. Well, as I have said, numerical results are in progress, not only for the Navier-Stokes equations, but also for Boussinesq, variable density systems, etc. And finally, let me say that an interesting question would be also to present and to deduce something similar in the case of boundary controls, in the case in which we control the system from the boundary. And I'm going to stop here. Thank you very much for your attention.
Thank you so much, Dr. Fernandez-Cara, for your excellent talk. Now it's time for question. Is open audio and video for question. Ten question, no chat, Professor. No chat, one question, no chat.
Okay. in the chats I have found two questions. No, one question says that thank you very much for this presentation. For the open questions in these problems, are there any results for local controllability? Okay, yes, this is I should have said yes, local controllability is ensured. It's true. This is one of the first results that have been obtained for the Navier-Stokes and Mucinex systems. The local controllability is ensured. The local controllability is not so difficult because what do we do in order to prove a local controllability? What we do is to apply, to linearize in some sense. We linearize the system. Then once the system is linearized, we go to the what we need is the controllability of the similar linear problem, like Stokes problem or something like this. And in that case, it is known. There are many ways to see this. It is known that the results are true because in that case, the control is, how can I say, is furnished by an observability inequality. And the observability inequality itself is proved using Kahneman estimates. All this has been worked first by Fursikov and Manuvilov, and then by Manuvilov, Jean-Pierre Puel, Sergio Guerrero, and myself along several years. So local controllability is not a problem. The problem is if you have an initial data that is very large, is it possible or not to make the solution go to a point that is far from the initial data?
Thank you, Professor. Any question or commentary? Or other question? I have one curiosity, Professor. You have some commentary or hierarchical control result for Navier-Stokes equation?
Can you repeat, please? A comment?
Result on hierarchical control for Navier-Stokes equation?
Yeah, hierarchy. This is interesting. This is interesting, an interesting question. What is hierarchical control here? It can be described as follows. We have two controls. We have a first control that solves an optimal control problem. So with this first control, what we do is to minimize a functional. And then we have a leader, more important control that tries to, once you have minimized a functional, tries to drive the solution to zero. So we can do this following what is called the Stackover strategy, in which one thing is done depending on the leader, and then the leader drives the system to zero. This has been done for a lot of systems, for parabolic equations, hyperbolic equations, systems, non-scalar systems. But in the case of the Navier-Stokes, and even in the case of the Stokes system, it is complicated because when we try to do this, we don't have estimates good enough to prove what we need. What we need would be an observability inequality for the linearized. We don't have estimates because of the fact that the pressure introduced a difficulty. So we are working on this, but for the moment it's not finished. Okay, even for the Stokes equation, it is a non-trivial question.
Yes, thank you, Professor. Any question or commentary? Luis Yapu, in chat, Professor? No chat.
Yeah.
Other question?
Okay, the ghosts are some kind of controls. No, the ghosts are not some kind of controls, unfortunately, because they are they are defined in the whole set. They are small, F epsilon and G epsilon are small, but they are not defined in a small set. And it is not realistic to assume that something that is defined on the whole domain is a control, because we cannot control a system acting on the whole system. It is not realistic. So unfortunately, although they are small as we want, they are not. They cannot be viewed as controls.
Thank you, Professor. Any question or commentary? Other question? Well, if there are no more questions, thank you again, Dr. Fernandez-Cara, for your amazing talk, and see you in other opportunity. Duban, please.
Thank you
Thank you
very
very
much.
much. Thank you very much, Professor Limac, for chairing the session of Professor Enriquez Cara. Professor Enriquez Cara, thank you very much for accepting our invitation. You are always welcome to our activities in ICMA in Latin America.
Thank you very much for you.
Thank you. So now we will have a break of 1 hour, and then we will continue with the talk of Professor Jenny Fragnelli. Thank you very much.
Bye-bye.
Bye-bye.
Hi, Diego.
No, Juan.
Perfecto.
Sí, sí.
Ah, excelente, excelente. ¿Está en Sevilla?
Sí.
¿Cómo está el clima por allá?
¿Cómo está qué?
¿O clima? Ah,
Hi.
good afternoon,
Hi.
Professor Jenny Fragnelli.
Hi, how are you?
Thank you very much again for accepting our invitation.
For me, it's a pleasure. Thank you for the invitation.
The Professor Diego Souza will introduce you.
Okay.
Diego is professor in University Sevilla.
Very well, thanks.
You will test slides.
Yes. Okay. You can see.
Excellent, excellent.
Okay.
Diego. We start in 5 minutes approximately.
Okay, yes. So I can. Is it hot there or not? Not yet.
Yes, yes. Is
In Italy, it's very hot.
Yeah.
Yes.
Here in Seville also is very hot.
is Diego in Seville now? Ne?
In Spain.
Yeah.
Diego? Sí.
Yes. So here is very hot. I think that we are on 35, 32, 35.
Also in
In
Italy.
Rio 30.
So here it's 12 in the morning, and then during the day it's very hot. 30, 35.
Wow.
In Rio
No.
13 degrees, but the sensation thermic is 8.
I also.
Oh.
So Jenny, you move from Bari to New Rome, right?
Yes, I take this position in December 2021, so about 2 years ago.
Ah,
It's in Viterbo, near Rome. It's 70 kilometers from Rome.
very good.
Diego, professor. I start. Well, good morning, everyone. To continue with ICMAM Satellite Conference on Analysis and Partial Differential Equation, now we have to Professor Diego Souza introduce to Professor Jenny Fragnelli. You can start, Diego, please.
Okay, thank you. Thank you very much, Juan. So for me, it's a great pleasure to introduce Professor Jenny Fragnelli. Professor Jenny Fragnelli is, she moved in 2021 from Bari to the University of Tuscia. Yes, thank you. And she's a specialist in degenerate and delayed and equation with delay. And today she's going to talk about controllability and stability for degenerate beam equations. So thank you very much, Professor, for accepting our invitation, and you have the word.
Okay, thank you, Diego, for the introduction. Thanks to all organizers, in particular to Professor Di Marco for this kind invitation. In my talk, I will speak about two problems. The first one is the controllability for a degenerate beam equation, and the second one is the stability for the same equation. And these results are obtained in collaboration with Alessandro Camassa, who is a PhD of mine from the University of Bari. So the first problem is the controllability one. The prototype that we have in mind is the the following one, where t is the time, so it's strictly positive. Then the state variable, the space variable x, belongs to a bounded interval of R. For example, we can consider 0, 1. Then the equation is degenerate, since here we consider the power x to alpha, and alpha is strictly positive but less than 2. I will explain later why we assume this condition. Then at 0 we consider a Dirichlet boundary condition, and at 1 we consider a control. The reason why we consider the previous equation is the following. It is well known that the Euler-Bernoulli beam equation can be rewritten as an equation of this type, where u is the vertical displacement, the derivative of u with respect to t is the velocity, then the derivative of u with respect to x is the rotation, and the second derivative of u with respect to t and x is the angular velocity. Rho here is the mass, and the quantity EI is the rigidity coefficient. So if we divide by rho, we have the following equation, where the function A is the following function. So if we assume that rho is very, very large at a point, say at x equal to 0, we say that the equation is degenerate. Degenerate. So this is the reason why we consider this problem, where A is a general function that is 0 at 0. And we consider the following problem. So the null controllability. We fix the time, capital T, and we want to find the control F such that the solution and its velocity at time t are 0 in the whole domain. Since the problem is, since we have a problem of second order in time, it is not surprising that we require these two conditions. And but I come back on this problem later. So before going on, I'd like to fix the problem in the reference bibliography. So if we have a parabolic problem, then null controllability means to find a control such that only the solution at time capital T is 0 on the whole domain. So if we consider a control localized at the boundary and the function degenerate at 0, so here the control is localized on the non-degenerate point, null controllability is studied in a paper in collaboration of Alabo and Cannarsa. Recently, Biccari, Hernandez Santamaria, Evan Costenoble studied the null controllability for the same problem, but here we have the power, and they consider only the case when the exponent is strictly less than 1. And the control in this case is localized at the degeneracy point. Clearly, if the control is localized in the interior, then there are a lot of other results. If A, for example, is strictly positive, then here there is a list of papers that deal with the null controllability. Here in this paper, A is regular. In this other paper, A is not too regular. The first result that we have when the equation is degenerate, in the sense that the function A degenerates somewhere, is negative, in the sense that one can prove that for this kind of equation, where, for example, we consider the prototype, then null controllability fails. Indeed, we can rewrite the simple equation as an it equation on an unbounded domain. And we can apply a result of Miku and Zazua, according to which for the it equation on an unbounded domain, null controllability fails due to the fact that the it equation holds on an unbounded domain. The control acts on a bounded domain, so an unbounded domain is left without control. So we can obtain that also for our case, null controllability fails. The only result that we can obtain if we consider the power and the exponent is greater or equal than 2 is regional null controllability, in the sense that we can control the solution, not on the whole domain, but only on a subdomain that is far away from the degeneracy point. Clearly, if the null controllability holds on the whole domain, we have a stronger result, since if we stop to control the solution at time t, then the solution is still equal to 0 if we take a time greater than capital T. And so it is important to prove global null controllability. And indeed, if the exponent is less than 2, one can prove that null controllability still holds if the degeneracy point belongs to the boundary, so is 0 or 1 in this case, or is in the interior of the space interval. Okay, if we consider a hyperbolic problem and assume for the moment the non-degenerate case, null controllability means to find a control such that not only the solution but also the velocity at time capital T is 0. And the reason is the following. So we have a wave from the left, a wave from the right. So if we require that u at time t is 0, then the waves collapse in the middle. And if we do not require that the velocity, also the velocity is 0, then the vibrations start again. So we have to require also this condition. And due to the finite speed of propagation, we cannot obtain null controllability for the wave equation for any time t, as we have seen for the parabolic case. For example, if we consider the non-degenerate case in 1D, we have that null controllability also if t is greater than 2. Now, if we consider a control localized in the interior, then null controllability is studied, for example, in these papers. There are two papers of Privat, Relanzo, Azua, where they consider also other problems. Then there is a paper of Wazara, where the author considered the semilinear problem. The paper of Sengoga, where the author considered two moving endpoints. In this last paper, we have also a moving control. But the equation is always non-degenerate. The first result where the equation is degenerate and in divergence form is due to Alaboca, Nars, and Logering, where they consider a generical function A that is 0 at 0. In the same period, Zhang and Gao proved null controllability for the prototype, so for x to k with another technique, and they prove that null controllability holds if k is strictly less than 2, and fails if k is greater or equal than 2. Then there is this other paper where the control acts in the interior of the domain. I recall also the paper of Gouye, where the author considered the power. Again, the exponent is less than 1, but the control this time acts at the degeneracy point. And then we have these other two papers. In the paper of Kogo, Kupenko, and Leugering, we have two controls that act at the boundary points, and the degeneracy is in the interior. Then there is the paper of Momni and Sali, where they consider the degenerate equation plus a singular term. They consider a control that acts on the degeneracy point, which is a moving point. And but they do not consider the case alpha equal to 1. But we will focus on the paper of Alaboca, Nars, and Logering. I told you that it is the first important one. They consider a general function A, which satisfies this condition. And they prove null controllability if this constant is strictly less than 2, and if it is greater or equal than 2, then they prove that null controllability does not hold. The first paper that deals with a non-divergence case at the degenerate equation in non-divergence form plus a drift term is the following paper in collaboration with Botayamu and Mugnai. And in this paper, we assume that A satisfies the same assumption as in the paper of Alaboca, Nars, and Logering. Then on B, we require that B is a continuous function and B over A is integrable. And we prove again that if the constant is greater or equal than 2, null controllability fails. If the constant is strictly less than 2, then we can obtain null controllability if T is sufficiently large. Now we come back to the beam equation, to the non-degenerate case. And null controllability is studied in a lot of papers. Here there is a list of some papers. But in any case, we have that the function A is strictly positive. And so this is the first time that the degenerate beam equation is considered. And as for the wave equation, we have that null controllability is related to the observability problem for the following homogeneous adjoint problem. So in particular, we say that this problem is observable if and only if this constant is strictly positive. The inverse of this constant is the cost for controlling the solution at time capital T. So as a first step, one has to prove that we have a solution. So there exists a unique solution. To do this, we assume on A the same assumption that we have in the paper of Alaboca, Nars, and Logering for the divergence case, or in the paper with the Botayamu and Mugnai for the non-divergence case. So we say that A is weakly degenerate if this constant is strictly less than 1, otherwise it is strongly degenerate. And in order to study the existence, we have to introduce suitable Hilbert spaces. So we consider the following L2 space with the weight 1 over A. So we consider the function L2 such that this integral belongs to R. Then we consider the space HI 1 over A, which are the intersection of L2 1 over A with the usual H1 0 space. And we consider the operator A given by A times the 4 derivative of U with this domain. Then we consider the following product space with this inner product, and we consider the following operator matrix. And we prove that this operator is non-positive and generates a strongly continuous semigroup. Actually, to prove this result, it is sufficient to require weaker assumption on A. It is sufficient to require that A is a continuous function, A is at 0 is 0, and this function is non-decreasing near 0. But if we assume that A is weakly or strongly degenerate, this condition is satisfied not only near 0, but on the whole domain. So we can apply these results. And so we rewrite the problem, the adjoint problem, as a Cauchy problem. And using the semigroup technique, one can prove that there exists a unique mild solution of the adjoint problem. And this solution is classical if the initial data is more regular. Now, we consider the observability. I recall you that the problem is observable if and only if this constant is strictly positive. So we have that there exists a solution, and now we have to define a good energy. In this case, as energy, we consider the following one. This is the energy associated to the adjoint problem. And we prove that this energy is a constant in time. And we can prove this fact just requiring the basic assumption on the function A. Now, in order to prove the observability, we have to prove an inequality like this one. And we can prove it assuming that A is weakly or strongly degenerate. And in this case, the constant C is the following one. So if this term is strictly positive, we have that the adjoint problem is observable if capital T is strictly greater than this quantity. So here we can see why we assume that the constant Ka is strictly less than 2. So it is a technical assumption. And moreover, we can also to estimate the cost for controlling the solution. Thanks to this inequality, we can prove the following null controllability result. I'd like to give you just an idea of the proof. So we consider the bilinear form, the following bilinear form, where V and WV are the solution of the adjoint problem associated to the following initial data. Thanks to the previous inequality, we have that this bilinear form is coercive. Now, to prove that lambda is continuous, we have to prove an inverse inequality. And we can prove this inequality, assuming again that A is weakly or strongly degenerate. And in this case, the constant C tilde is the following one. So we have that lambda is continuous and coercive. Now we consider the functional capital L given in this way, and we can apply the Lax-Milgram theorem. So we know that there exists a unique solution of the following equality. Now we consider the function f equal to the second derivative of V bar with respect to x, where V bar solves the following adjoint problem, homogeneous adjoint problem. And we know that there exists a solution of this problem thanks to the existence theorem. Now, to prove the null controllability, we use the solution by transposition. So we prove that there exists a solution of transposition, a solution by transposition of the original problem. And if U solves P with F given in this way, we can prove that U and its derivative at time capital T is 0 on the whole domain. Now we consider the second problem, so the stability for the degenerate beam equation. The prototype is the following, so is the same equation as before. At 0, we consider the Dirichlet boundary conditions, and at 1, we consider not control, but these two conditions, where beta and gamma are non-negative constant. These two conditions are not so strange. Indeed, if beta and gamma are 0, then we have two conditions that are similar to the following two conditions at 1. These two conditions are the conditions that one can use to study the stability for the Euler-Bernoulli beam equation. And these two quantities, so EI, the first derivative of U, and EI, the second derivative of U, have an engineering meaning. In particular, we have that EI and the second derivative of U with respect to X is with minus is the bending moment. And minus EI and the further derivative of U with respect to X is the shear. So these two conditions means that the shear is negatively proportional to the velocity, while the bending moment is proportional to the angular velocity. So we consider the following problem. So we want to find, we look for conditions such that the energy associated to the original problem is goes to 0 if t goes to infinity. Also, in this case, I'd like to frame the problem in the reference bibliography. So if we consider ordinary differential equations or a system of ordinary differential equation, then the asymptotic stability is studied in these papers if f is linear or f nonlinear. In all these papers, we have that the damping is non-negative. If we consider a hyperbolic partial differential equation and the damping is strictly positive, then we have this, for example, this paper where the author considered just the linear case, so f is 0. Then there is a paper of Zhang where f is nonlinear with linear growth. And in this other paper, the function f is a generic function. Now, if we consider a parabolic case where the damping is integrally positive, on off, positive, negative, or distributed or localized with the delay, then there are a lot of other papers. Here there is a list of papers. There is also 2 books, one of Alabon Bossai and the other of Bassin Coron. But in all these cases, we have that the equation is always non-degenerate, since here we have the Laplacian of u. So if the equation is degenerate but in divergence form, the stability of this equation is studied in the paper of Alabon, Canars, and Logering, where I recall you that A is a general function, A can be weakly or strongly degenerate at 0. And at 1, they consider the following condition, where beta is a strictly positive constant. This, if the problem is in non-divergence form, the stability is proved in this paper in collaboration of Mugnai, that will appear in Advances in Differential Equations in 2027. And again, here we assume that A is weakly or strongly degenerate, and A at 0 is equal to 0. In this case, the condition that we have at 1 is this one, which is similar to the previous one, so to the one considered by Alabon and Canars and Logering. In this case, we have here the function eta, which is related to the drift term and to the degenerate function A in the following way. And the constant beta can be also equal to 0, so it is non-negative. And now we consider the beam equation, the Euler-Bernoulli beam equation. For this kind of equation, the stability is studied in these 3 papers of Chen and other mathematics. And there are also other papers where the stability of this equation is studied, but with a degenerate damping. This is the first time that the stability is studied for a degenerate equation, degenerate in the sense that the coefficient in front of the fourth order derivative is 0. And I recall you that in this case, beta and gamma are non-negative constant. So we have again to study the existence of a solution. In this case, we do not consider the adjoint problem, the homogeneous adjoint problem, but we consider directly the original problem. And I recall you that in the original problem, this time, we have the Dirichlet boundary condition only at 0, not at 1. So we have to introduce other Hilbert spaces, which are different from the previous one. In this case, we consider so this space K1 1 over A and K2. So we in this space we have only the two conditions at 0. The operator is the same as before, but the domain is different. As a product space, we consider the following one with this inner product. So the sum of the two integrals are the same as before, but now we have to add these two conditions due to the boundary conditions that we have at 1. Again, we consider the operator matrix, this operator matrix with this domain. So in the domain of the operator, we find the two conditions at 1. And we prove also in this case, assuming the basic assumption on the function A, that the operator is non-positive and generates a strongly continuous semigroup. And so we can prove that there exists a unique mild solution of the original problem. And this solution is classical if the initial data is more regular. So now we have to consider the energy, and we consider the energy this time associated to the original problem, not to the adjoint problem. So here we have this quantity, the red quantity is the same as before, but here we have to add these two terms. Beta and beta u to 2 and the gamma times the derivative of u with respect to x to 2. Then again, assuming the basic assumption on the function A, we have that the energy, the derivative of the energy satisfies, is given by these two terms, by the sum of these two terms. So it is negative. This means that the energy is non-increasing. In particular, we have that under the same assumption as before, so if A is weakly degenerate or strongly degenerate, we have that the energy goes to 0 exponentially according to this law. Also in this case, I delight to give you an idea of how proving it. So the idea is to use this lemma, this result, that we can find, for example, in the book of Komornik. According to this lemma, if the energy is non-increasing, and if the energy satisfies this inequality, then decays exponentially according to this law. So we know that thanks to the previous theorem, we know that the energy is non-increasing. And so to prove that the energy decays exponentially, we have only to prove this inequality. And to do this, it is important to prove the equivalence between these three norms. This is done thanks to the following Hardy-Poincaré inequality, proved in a paper in collaboration with Cannarsa and Rocchetti. Then, thanks to this equivalence, we can prove that the following variational problem has a unique solution. This solution satisfies these two estimates, belongs to the domain of the operator, and satisfies this problem. So now the idea is to use this lemma, this variational lemma, with the lambda equal to u at time t and position 1, and with me equal to the derivative of u with respect to x at time t and position 1. And so thanks to this lemma, one can prove that if we have a classical solution of the problem, then this solution satisfies this inequality. So we have that the sum of these two integrals can be estimated by the energy plus the integral of the energy. Thanks to this inequality, one has that there exists a constant, epsilon 0, such that the integral of the energy can be estimated by the energy plus the same integral. So if we move this term on the left, and if we choose delta such that delta is strictly less than epsilon 0 over C6, then we have this inequality. And if capital T goes to plus infinity, we have exactly the inequality that we need to conclude that the energy decays exponentially according to this law. Okay, so now recently we have proved null controllability and exponential stability for the problem in divergence form. In this case, if we consider the controllability problem, we have at 1 the following condition. So u at 1 is 0, and the derivative of u with respect to x at 1 is equal to a control. If we consider the stability problem, we consider at 1 the following two conditions, where again beta and gamma are non-negative constant. But contrary to the problem in non-divergence case, at 0 here we have different conditions. For example, if A is weakly degenerate, we require that u and the derivative of u with respect to x are 0 at 0. If A is strongly degenerate, then the condition on the derivative is substituted by this other condition. And this is not surprising, since also for the parabolic case, when we have the divergence form, we have two different conditions at 0. One in the weakly degenerate case and the other one in the strongly degenerate case. So now one can think to obtain controllability and stability results for the problem in divergence form, from the results that we have proved for the problem in non-divergence case. Indeed, one can rewrite the operator in divergence form as an operator in non-divergence form, adding these two terms. But if we rewrite the operator in this form, and if we want to apply the previous results, we need to make additional assumption on the function a. For example, we have to add a condition on the second derivative of a. But I recall you that for the problem in non-divergence case, we assume that a is at maximum C1, not C2. Moreover, another problem is the following. So the natural space for the problem is in a divergence form is not the weighted space L2 1 over A, but it is the natural space L2. So we are forced to study controllability and stability for the problem in divergence form independently from the one in non-divergence form. And clearly, the Hilbert space are different from the previous one. For example, if we consider the controllability problem and A is weakly degenerate, then we consider this space V2A. So U prime in this case is absolutely continuous. Then we have this condition on the second derivative, and U at 0 and at 1 is 0. If A is strongly degenerate, then U prime is only locally absolutely continuous. Then we consider the operator AU in divergence form with this domain. So here we find the other condition, so the condition on the first derivative, or on the second derivative in the case that A is strongly degenerate. And again, we prove that the problem, the adjoint problem, has a unique solution. We define the energy of the adjoint problem in this way. So here we do not have the weight for the derivative of y with respect to t, but we have the weight A in front of the second derivative of y with respect to x. And also in this case, we prove that under the basic assumption on the function A, the energy is constant. Then, using again the solution by transposition, we prove that the original problem is null controllable. In this case, we have that the adjoint problem is observable if t is strictly greater than this time. Observe that also in this case, we have this condition, so we have 2 minus Ka. So again, we have to require that the constant Ka is strictly less than 2. Now, if we consider the stability problem, we have to consider different spaces, as we have seen for the problem in non-divergence form. So if A is weakly degenerate, we consider here only the condition at 0. And if A is strongly degenerate, we consider these other spaces. Again, we consider the same operator in divergence form with a different domain. Here we do not find the conditions at 1. As the product space, we consider the following one, and we consider the following operator matrix with this domain. So in this domain, we find again the 2 conditions at 1. So now, if A is weakly or strongly degenerate, we prove that the original problem, and not the adjoint problem, has a unique solution in a suitable space. Then, as energy associated to the original problem, we have the following one. So again, these 2 terms are the same as before for the controllability problem, but here we have again these 2 terms which are related to the boundary condition at 1. We can prove that the energy also in this case is non-increasing, and we prove that if beta and gamma are strictly positive, then the energy goes to 0 exponentially according to this law. We are able to prove this result even if beta and gamma are 0, but only for the weakly degenerate case. since in this case we are able to estimate the derivative of u with respect to x at 1. If in the strongly degenerate case, this is an open problem. So in the last minutes, I'd like to conclude with some open problems and the work in progress. So now there is, we are studying with Alessandro Camasta and Cristina Pignotti from L'Aquila, the stability for degenerate wave equation in divergence and in non-divergence form, and also for degenerate beam equation in divergence or in non-divergence form with the nonlinear term in the equation, say superlinear, and a damping with the delay. Another work in progress is the following. So always with Alessandro Camasta and Muhammad Akil, we are studying the stability with the local degenerate damping, but we are considering only the degenerate beam equation. And then we are studying the controllability for the degenerate beam equation for arbitrary short time. Indeed, in 1994, Komornik proved that for non-degenerate beam equation, null controllability also for arbitrary short time. Clearly, I recall you that for wave equation, this is not possible. But now we are trying to prove the results of Komornik for degenerate beam equation. And this is a work in progress with Muhammad Akil and from Valenciennes and Ibti Sam Issa from the University of Bari. Now, just to conclude, some open problems. So I told you, and I underline more times, that the assumption Ka strictly less than 2 is a technical assumption. And so the problem is to obtain controllability and stability if this constant is greater or equal than 2. So for the degenerate wave equation, we have that null controllability fails. But for the degenerate beam equation, we are working on it. And it is also interesting to study controllability and stability for this kind of equation, so for the degenerate beam equation, with a singular term. There are two papers in collaboration with Dimitri Mugnai and Amin Sbai for the degenerate wave equation with a singular term, but there are no results for the degenerate beam equation with a singular term. Then it is also important to study the controllability for the degenerate beam equation if we have a control on the degeneracy point or a control localized in the interior of the domain or a bilinear control. So we can, for example, adapt the results by Cannassa, Cristina Urbani, and so on, Alabo, for the parabolic case. And then it is also important to see what happens if we have a moving control. And as I told you before, there is also the stability for the problem in divergence form in the strongly degenerate case when beta and or gamma are equal to 0. So that's all. Thank you for your attention.
Thank you very much, Jenny, for this very nice talk. So now we open the turn for comment questions. So if anyone has some question, please just ask the question. Okay. So let's see if someone.
There is a
Yes.
question in the chat.
There is a question in the chat. So is Fawad Tari. He say, thank you very much. Concerning the generate heat equation in the divergent form with a diffusion coefficient that vanish at the whole boundary. I think that he's saying about the high dimensional. Are there?
So for the one-dimensional case, there are some results. For the n for higher dimension, so 2, there are no results. There are no results. Also for if A degenerates at some point, not on the full domain, but just on a part, there are no results.
Okay. So I have a question. Is about the distributed control. I mean, all the result that you show us is boundary control. Yes.
Yes. So for
And
the distributed control, for the generate beam equation, there are at the moment there are no results. This is a new argument, so there are no results. For non-degenerate beam equation, yes. Also for non-degenerate for wave equation.
yes, because I'm recalling some result by, I don't know if you know, the result by Enrique Fernandez Cara, Fagner Diaz Araruna, and Sergio Vasconcelos, where they treat the heat equation with the degeneracies, okay? And they prove for the heat equation some controllability result with in the distributed case, okay? And if the domain touch the degeneracy, so they can solve the problem for alpha larger than 2.
For the parabolic case.
For the parabolic with degeneracies, yes.
Yes, thanks. I
can send you the papers.
Yes.
And this is because when you have the domain that touch the boundary, and you make the transformation to the heat equation in the whole domain, so you have a control region for the heat equation, the unbounded domain, with a control in the stereo domain. So, and then you can control it, the heat equation.
But the control region touch the boundary in the degeneracy point?
Yes,
or...
exactly. Okay, I have another. Is there other question here? Alex Imba. He say that thank you for your presentation. What technique do you use to proving observability inequality for the generate Euler-Bernoulli beam equation? Could be this technique extend to the multidimensional case?
So the technique is a multiplicative technique. Okay, so I think that we can adapt, but we have to estimate. There are some problems to estimate some terms. So I don't know in the n-dimensional case it is possible. I think there are the same problem as in the one-dimensional case.
Okay.
Okay, so.
Okay.
Please, I have a question.
Okay.
Thank you very much.
Go
Thank you
on.
very much, Professor. just for the control region, I observed that we can act on a small region, omega, small omega, or on just 1 point. My question, it is possible to take a small region, not only on space, but also in time.
The contrary. So I know that there are some results. So the control, the control, so there are some results when the control is moving in time. Okay. You mean this?
Not moving in time, but the control is active only on a sub interval of 0t.
I do not understand. The control acts?
Just on a small interval of 0t. Small region in space and small region in time, if we can say it.
I don't know. I don't know. I never see this control, so I don't know. But it's interesting.
Thank you very much.
Okay, I have another question. Is that I mean, there is a method, no, the transmutation method, which allow you to pass if you have a control result for the heat for the wave equation, then you can obtain a result for the heat equation, right? Is the transmutation method. So yes, you have a fourth order beam equation. So could you use a transmutation method to obtain some result for the Kuramoto-Shibashinska equation, which is a parabolic fourth order equation using the transmutation?
I don't know, Diego. I have no idea, but it's a very good question. I don't know.
Because I never see this transmutation method applied for let's say degenerate equation. But, and maybe it's interesting to.
Yes, I think that it is interesting
to see if it is possible.
Yes.
And also, my last question is related with a comment that you mentioned at the end. The result that you present is the control act the non-degenerate part, right? And but you also mentioned that for the heat equation with degeneracies, one may there is a recent result by Vicari where they treat the case where the control act on the.
Yeah. Also for the degenerate wave equation, there is the paper of Guyer, where the author considered the power. Yeah. And also in that case, we have that the exponent is strictly less than 1, so the weak degenerate case. So I think that also for the degenerate beam equation, we are able to study this case. Okay. The problem is the strong degenerate case.
Okay. So I am very happy to see that the discussion is very active, also very interesting. Maybe we have space for our.
Yes. So you want to ask a question, Duvan, or
no? Please.
okay, we can finish here. So thank you very much, Jenny, for this very nice talk. And
Thank you to you also for the comments and for the suggestion.
Okay, so I give the word to Duvan. So thank you, Duvan, also.
Thank you. So thank you very much to Professor Sousa for sharing the session, Professor Fragnelli, and of course, thank you, Professor Fragnelli, for your very interesting talk. You are always welcome to our activities in ICMA and Latin America. So we have with us our next speakers. I will pass the chairing to Brian Grajales.
Thank you, Duan. Professor Krieger, maybe you can share your screen.
Yes.
See if you could. You can.
Is that okay? Can it be seen?
Yeah, we can see. Okay. Perfect. So it is my pleasure to present Professor Joachim Krieger from Swiss Institute of Technology, Lausanne. Professor, thank you for being here. Thank you for accepting our invitation. It is really an honor to have you here. And Professor Krieger is presenting his talk entitled Global Controllability of a Geometric Wave Equation. Go ahead, Professor. Thank you.
Well, thank you very much for the invitation to speak at this event, which is I feel very honored to do so, and I'm very happy about this opportunity. So I will talk about joint work with Jean-Michel Coron from Paris and Shenkong Xiang from Beijing, recent work. And it's also in the context of controllability of certain wave equations, but it seems to me like to us that these sort of wave equations have not yet been studied from this viewpoint. And so this talk is maybe a bit of an advertisement also for these kind of questions, which seems to have lots of interesting connections to do topology analysis and so on, and recent developments in dispersive PDE. So to set things up, first I consider a sort of a general nonlinear wave equation. Box U is a function of U and the first derivatives of U, so I'm not looking at quasi-linear equations. Box for me is always minus dtt plus the Laplacian. And at the beginning, I will assume that x, so U is a function of t and x takes values in compact Riemannian manifold, but for most of my talk, actually, this manifold will be very simple. It will just be the circle. But for now, for this introduction, let's assume that M is a general manifold, and omega is a small open subset in M, which we can think of as a small open disk. And so we could consider the problem of control, exact controllability, as well as stabilization of this kind of equation. So again, by exact controllability, I mean that so there is a time t associated to this manifold M and this open set omega, such that for any data pair U0, U1, so it's a wave equation, so we have to impose two functions at time 0, say, and a terminal data pair at the time t, there is a forcing function g of t and x, which is supported on omega with respect to its x dependence, and such that the forced wave equation evolves the initial data u into the final data v. Okay, of course, you can then ask in which topology, and so I will, throughout this talk, I will always assume I work in the H1 topology for my data, and the function g is then going to be chosen in L2. Similarly, there's the issue of stabilization. So here the issue is there a control function which is again supported in this set omega in M, such that if you look at the forced evolution with arbitrary initial data of energy class, say, these data are going to, the evolution is going to decay exponentially. And more precisely, typically we want G to only depend on Tx as well as the value of U at time t and the value of the derivatives of U at time t. So a closed loop type situation. But for much of the talk, actually, G of t and x will be very simply to be A of x times ut, so damping stabilization, where A is a function which is, it's, let's say, C0 infinity and supported in omega and non-negative. And so the question is, can we achieve damping stabilization? Now, of course, for the linear wave equation, so if there's no nonlinearity at all, it's very classical that these concepts are closely related. And of course, I mean, I should mention in this talk, although it's strictly speaking, not about this subject, but there's this very famous geometric control condition, which says that so for the linear wave equation without nonlinearity, if the set omega is such that any geodesic traveling at speed 1 meets omega within a certain fixed time t, no matter where it starts and in which direction it starts, so the geometric control condition, then it is true, by famous work by Rauch Taylor and Bardos Lebeau Rauch from the 1980s, it is true that we have exact controllability in the sense that there is a time t such that given two pairs of data, U0, U1, V0, V1 in the energy topology, there is a forcing term G supported in omega. It's L2 norm bounded by some constant times the energy norm of these data pairs, and such that we evolve the initial data U into the final data V. And similarly, there is the stabilization result. If the support of the function A satisfies the geometric control condition, and we look at the damped wave equation, then we have the exponential decay of the energy. Now, in this talk, again, so I will look at a very simple situation where the geometric control condition is vacuous and is trivially satisfied, namely my manifold M is going to be the circle and omega is just going to be a small open interval inside the circle. But my emphasis is going to be on the nonlinear term, actually. And so let me quickly review, again, there's a vast literature, of course, but it seems to us that most results on controllability and damping stabilization of nonlinear wave equations concern kind of a defocusing situations. So by defocusing wave equation, here is kind of the archetypal example. Box U is plus modulus U to the p minus 1 times U. Let's say if you're in a three-dimensional context, we have to restrict the powers that come up here to avoid energy supercritical situations where we know nothing about this wave equation at all. I emphasize the sign of the nonlinearity here, always keeping in mind that box has a plus Laplace involved. So I emphasize the sign here because that is exactly the kind of defocusing situation, which ensures that the natural energy associated to this equation is positive, definite. And this positive definiteness of the energy, it kind of prevents certain complex nonlinear phenomena from occurring, such as finite time blow-up, bubbling phenomena, or also non-trivial attractors, which could be an obstacle to damping stabilization. Now, so the strategy that typically is used to achieve controllability for these kind of equations is kind of a two-step method. First, one uses stabilization via damping to kind of simplify your data to make them and ensure that they have small energy because of the exponential decay of the energy of the evolution. And once one is in a small energy regime, one then implements a control step, which one can do if one has the geometric control condition for the linear equation, and then one uses a perturbative argument to kind of deal with the nonlinear contributions to get the controllability for small data. And then because it's a wave equation, of course, one can reverse the sense of time and one gets the controllability for arbitrary data in this way. And the key of this, of course, of this procedure is that stabilization reduces essentially to trivial or very small solutions where the control step is easy to implement. Now, again, there's a vast literature. So just to give some examples here, in the Schrödinger context, which is very similar also for defocusing nonlinearities, there's, for example, work by Deman, Gérard, and Lebeau from 2006. There is work by Deman, Lebeau, Zhuazhua from 2003. And there's also work by Zhuazhua, again, in this context, slightly different background. So he works on R3 in the complement of a ball, and the control is in the complement of a ball. But kind of it's this kind of philosophy that is appropriate to these kind of works. Now, so what I want to talk about here is sort of a different kind of nonlinear equation, which for some reason has not yet received much attention in terms of their controllability. And so these equations, they are very interesting, I think, from a mathematical point of view, but also from a physical point of view. So to motivate them, basically they're, if you want, the simplest kind of generalization of the free wave equation, but taking, instead of values in R or C, taking values in a manifold. So we want to have some kind of natural generalization of the free wave equation, but taking values in some kind of curved manifold N. And if one mults this over, one quickly arrives at the conclusion that the condition one should impose here on this wave equation, assuming that the target manifold is a Riemannian embedded submanifold of some Euclidean space, is that box U should be perpendicular to the tangent space of N at U. So this is the condition that characterizes wave maps, and of course is completely analogous to harmonic maps, where instead the condition is that Laplace U would have to be perpendicular to the tangent space of N at U. So for me, this talk, I will be mostly interested in a specific class of targets, namely the spheres, L-dimensional spheres, which I can view as submanifolds of RL plus 1. So then the wave equation that emerges if one works out, well, I mean, box U has to be a multiple of U, and that multiple is exactly given by this quadratic expression in the first derivatives of U. So it's a semilinear wave equation with a quadratic in the derivatives nonlinearity. Of course, formally speaking, it looks like a cubic wave equation, but because U always takes values in this compact target manifold, U is really of size 1, and so the nonlinearity is essentially quadratic. So there are some very closely related models, which I should mention. There is also the half wave maps equation. If your target is further specialized to be S2, then one can look at the equation UT is equal to U vector product, the square root of minus Laplace times of U. And this equation, it looks, of course, quite different than the wave maps equation from before, but it can be reformulated as a wave equation with a leading nonlinear term, which is identical to the wave maps term, plus some non-local additional terms. And there's also the Schrödinger maps equation, again, kind of the Schrödinger analog of wave maps. UT is U vector product with Laplace U, sharing many of the analytical features of the wave maps equation. And I mention these two related models because they have particular applications to describe magnetization of ferromagnets. So I will mention a couple more references to the actual physical applications of these equations. The wave maps equation is, you can think of as a relativistic analog of the Schrödinger maps equation, should also have physical applications. Now, so the question I want to discuss, start to the analyzing here is the wave maps problem with domain M times R, where M is a compact background manifold, and for me, mostly S1, and target N, is this controllable? Now, so to phrase this problem correctly, you have to sort of make the correct definition here. So of course, if you simply add an arbitrary forcing term to the nonlinearity here, then you will get an equation which is not very well behaved, because you will not map into the target anymore if you just use an arbitrary forcing term. And if you don't map into the target anymore, then you will lose the a priori boundedness of your evolution. And without the a priori boundedness, you will probably get explosion in finite time. And so it's not a well-behaved equation. So you want to make sure that your forced system still maps into your target manifold. And that's why instead of just a generic G, you have to project this G into the direction that's perpendicular to you, provided you work with target SL, which I will do for most of this talk. So the controlled wave maps evolution with target sphere is given by this equation that I've displayed here. And so G is a generic, is a function taking values in L+1, but in the control problem, we have to project it into the direction that's perpendicular to you. Now, for this equation, you can check that if you take arbitrary data, which are sort of geometrically correct in the sense that at time 0, U maps into the sphere and the time derivative maps into the tangent bundle of the sphere, then you can easily verify that the evolution is going to map into the sphere always. And you can then ask the question, well, is this kind of model controllable in the sense that given an initial data pair and a final data pair, again, correct in the sense of this last line here, can we find a control that maps the initial data into the final data? Now, what is the motivation behind this? As I said, it's kind of, in some sense, the simplest generalization of the free wave equation, but taking values in the manifold. It has very interesting, this kind of wave maps equation displays interesting nonlinear phenomena, such as soliton type phenomena, finite time blowups, which are being investigated very closely. And moreover, as we'll see in this talk, the issue of global controllability is actually closely linked to certain non-trivial topological features. And these topological features, I mean, we are just scratching the tip of an iceberg here, and I think there's much more to be discovered here, particularly in the higher dimensions. My talk will mostly concern the simplest case, which is in one spatial dimension for the background. Also, a full resolution of this issue of controllability of the wave maps will have to use all the sophisticated analytical tools that have been developed recently for the uncontrolled problem, such as the soliton resolution property and similar things. And there seems to be a rich trove of new analytic questions which may require new developments of new tools to actually answer. And I hope to present some of these questions that interest me later on. Now, again, as I said, in this talk, I will only be able to handle the most basic case, namely of a background M, which is S1. But already in this case, there are difficult questions that occur that are open that we don't know yet how to answer. So I said I wanted to talk about some more physical motivation here. So there's a very recent paper by two mathematicians from an Indian technological university, actually, and they mention magnetic sensors, data storage devices, and actually even in medical sciences, Schrödinger maps and related models appear in magnetic nanoparticle hyperthermia as a kind of cancer treatment. So it seems that maybe this kind of questions even have some relevance in actual applications in the real engineering world. Okay, so now, more concretely, the model that I want to study now is controlled wave maps, as I have just said. But my background, I will simplify, is S1 times R. So X just takes values in the circle, and my target is going to be SL. L here, I allow values from 1, 2, etc. But mostly later on, L will be larger or equal than 2, because the case with L equal 1 is not that interesting. And so the kind of model that I consider is the equation that I've displayed here. And of course, because now my spatial domain, background domain is just one-dimensional, Laplace U just becomes UXX. So the equation is minus UTT plus UXX is equal to my wave maps nonlinearity plus a forcing term, which gets projected into directions that are perpendicular to U. Okay, so furthermore, assume that we are given some interval omega, some open interval in S1, and we impose the condition that the forcing term should be supported in this omega. And the question is this preceding problem globally exactly controllable without any restriction on the size and final data? So I'm not just trying to consider some kind of a local controllability result, which is perturbative, let's say, around the linear theory, but I really want to understand the global controllability of this problem. And the answer is very quickly no, because if you consider the S1 target, so L equal 1 case, then there is an obvious topological obstruction, because given an initial data pair U0, U1 from S1 into S1 times TS1, and a final data pair V0, V1, then of course, if I have exact controllability and I can sort of deform the initial data into the final data by means of this forced wave maps flow, then U0 and V0 had better be in the same homotopy class. And of course, this is not a priori given. So the best I can hope for in this case is controllability in the same homotopy class. However, when I take L larger than 1, so then the first homotopy group of the spheres vanish, and this obstruction disappears. However, as we'll see later in the talk, there are more subtle questions where other topological obstructions appear, and that manifest themselves also in certain analytical problems. So the result that we can give, the most general result now, is you assume that the target is a sphere SL with L larger or equal than 2. And then we have the theorem that controlled wave maps from S1 times R into SL are globally exact controllable in H1. And more precisely, given so an open interval in S1 and number M, which controls the H1 norm of the initial and the terminal states, then there is a time t and a constant c, and these numbers can be effectively computed in dependence of M. Although I have to say that the dependence that we have is not very good. It's more than exponential in size, such that there is a control function g supported in omega and in its L2 norm being bounded by c, such that the solution of the controlled wave maps flow starting at U0, U1 ends at V0, V1. So this is the first main result that I want to talk about and explain a bit of the proof. Now, let me comment a bit on this result. So there's interesting follow-up questions that one can ask. First of all, so I work in the energy topology here, but you could ask, can one lower the regularity requirements on the initial and final data? It is known that the wave maps system in 1+1 dimensions is well posed in H3/4 plus. So this is a result due to Kiel and Tao, I think, from the late 90s. And so one could ask the question, can we also get controllability at this lower level of regularity, which is quite likely. Again, like I said, the time t that one needs to affect this exact controllability is kind of poorly bounded as a function of M. But at least we can give an effective upper bound. However, we cannot give an explicit formula for the control function g. And as I will argue if I have time later in the talk, there is actually an intrinsic reason, which is sort of a subtle topological reason, why you cannot give a simple formula g for this forcing term, which achieves the control stat. There is also the question, which is very natural, if you can, well, reduce the time needed for exact controllability to just 2 pi plus epsilon, identifying the circle with the interval from 0 to 2 pi. The Huygens principle, of course, suggests that in principle, any time larger than 2 pi might be possible for the exact controllability, but again, this seems very difficult to prove something like this. And you can also ask, well, I mean, is there some kind of optimal way of achieving this control? And again, we don't know exactly how to do something like this, how to characterize an optimal control function. Now, so let me talk a bit about the strategy of the proof, which I think is quite neat, and it uses some kind of the structures that people have discovered in the analysis of this wave map system, in particular the null structures, but in a very, very basic, in a very simple way. If you try to do this in higher dimensions, then the analytic difficulties become much, much, much worse, and it becomes much harder to analyze this kind of equation. But in 1 + 1 dimensions, I think the approach is extremely transparent. So in principle, we try to follow the strategy that I outlined for the kind of defocusing setup before. We are given an arbitrary initial data, and we try to sort of simplify that data, ideally use a damping stabilization to make it small. And once it's small, we can basically use linear controllability to achieve the control step. Okay, so as a first step, we apply damping stabilization, and we arrive at the equation that I've displayed here. And if you do that, it's easy to check that if your data are adapted to the geometry, I mean, as I said before, then your evolved solution will always map into the sphere. The condition that ut is perpendicular to u will be preserved. So this is good. But by contrast to the defocusing situation, for this kind of flow, it's not guaranteed that you will converge to a trivial state. And this is due to the fact that there are non-trivial steady states for this equation. So non-trivial, non-vanishing solutions which don't depend on time. And these are simply the geodesics, the closed geodesics on SL, which are maps from S1 into SL, and which solve this equation but don't depend on time. And so what you can, what may happen is that starting with a generic initial condition, you converge towards some geodesic. And then, of course, different initial data sets may converge to different geodesics, and then it's not clear how to achieve the control step. So somehow, if you're in the situation where your evolution converges to a closed geodesic, which is not trivial, then there's something else you have to do. You have to stop the process, the damping stabilization process, and do something else to kind of move beyond this obstacle. That's the second step that we implement, is actually a control step near a geodesic, which pushes the energy below the energy of that geodesic. And once you have gone below the energy of the geodesic, you can resume the damping stabilization step. And by using the fact that, well, for the sphere, again, like it's very well understood what the closed geodesics are, their energy levels are quantized. Using finitely many iterations of this damping and then this extra control step near geodesics, we can indeed reduce to a situation where the energy is small, and then we can achieve the control step by simply using small energy controllability of the linear problem. So now let me give some details particularly for the damping step, and then for the control step near geodesic. These details, I mean, they're elementary, but they're kind of tricky, and so and I think they involve some interesting aspects. So let me try to give some details here. So first of all, of course, in analogy to the defocusing situation, well, we look at the energy, and we look at how the energy evolves under the damped wave maps flow. And we have this well-known identity here that E of t minus E of 0 is given by the double integral of A of x times modulus ut squared. And of course, our goal is to decrease the energy as much as we can. So we want the right-hand side to be as large as possible. But of course, again, if u is close to a geodesic, then the derivative ut is going to be very small, and the right-hand side may be very small, and then we don't achieve much in terms of reduction of the energy. Okay, so this is something we have to face, but the goal is to actually show that if the right-hand side here is very small, well, then we have to be in the special situation where u actually at some time at least is close to a geodesic. And once we're close to a geodesic, we use the other step. So how do we actually implement this? Well, first we introduce this concept of epsilon approximately geodesic data. So these are all data for this controlled the damped wave maps flow, such that there exists a closed geodesic, such that the geodesic data, which are just a pair gamma 0, are close to my data in the H1 topology in terms of this constant epsilon. So they're epsilon close in terms of the H1 norm to the geodesic data. And so now to quantitatively implement this intuition that I just said, we have the following proposition. So consider the damped wave maps flow from S1 times R into SL and assume that the initial data are bounded by some constant m. Well, then given epsilon bigger than 0, we have a dichotomy. Either this double integral, which describes the decrease of the energy, is larger than some constant delta 1, which I can actually write as essentially a power of epsilon. And the exponent q here is actually a function of m. Okay, so this is slightly complicated, but I suppress these details. Or else, if this first alternative doesn't hold, which means this double integral is very small, then there has to be actually some time within, okay, so I pick here the time interval from 0 to 32 pi. I mean, 32 pi is not important. I mean, you could take any kind of number here, which is larger than 2 pi to implement the step. So then in the alternative case that this double integral is less than delta 1, there is some time t in this interval such that your data at time t are epsilon close to geodesic data. And then how does one use this proposition? Well, you first fix a time interval 0, 32 pi, and you check, is this number larger than delta 1? If not, then you are in the case where you are in the case where your initial data is close to geodesic. On the other hand, if this number is larger than delta 1, well, then you repeat that step, right? So you go from 32 pi to 64 pi. And again, you check, is this number larger than delta 1? And if not, then again, you can pick some time t such that you're close to a geodesic. If not, you have increased this double integral now from 0 to 64 pi to 2 delta 1. And then you keep doing this. And eventually, either you have decreased your energy to a small size, or you have discovered a time t star where your evolution of the damped flow is actually close to a geodesic. So this is exactly what we want. So how does one prove this kind of result? Everything here is effective, right? So we are not using any kind of soft compactness arguments. We can really quantify everything here. So to prove this proposition, there's basically 2 steps. So the first step is some kind of quantitative, approximate, unique continuation type result. What does it mean? Well, it means an exact unique continuation argument would say that, let's say, UT vanishes in some narrow strip. Well, then you show that UT has to vanish everywhere. Now, I don't know that this actually vanishes. I just know that the double integral is small, say. Well, assuming that this double integral is small, I then have to conclude that UT actually is small everywhere on S1. And I will make this precise in terms of a lemma later on. And then the second step is an averaging technique to extract the approximately harmonic map that I was talking about from before. Now, so for this first step, to this approximate unique continuation step, we use a very special feature of the wave equation in 1 + 1 dimensions, which is, of course, the perfect symmetry between t and x. The beauty is that you can think of t as the time and x as the space variable, but you can flip their roles and you can think of t as the space variable and x as the time variable. So the following lemma then basically implements this approximate unique continuation step. So it says that if you use a solution of the damped wave maps flow with initial energy bounded by some number m, then there's some exponent such that if we assume that this double integral here, which describes the decrease of the energy under the damped wave maps flow, is bounded by delta times the energy at 0, then actually we can conclude that if you look at any vertical segment of length 3 pi, and you look at the L2 norm of UT on that segment, it's going to be small everywhere. So for no matter which x you choose, you look at the corresponding vertical time segment over that x, and you look at the L2 norm of UT, it's going to be small. Okay. So from some kind of average smallness information, we get some kind of punctual pointwise information. Now, again, so in higher dimensions, this kind of to achieve this kind of results is very difficult because t and x don't play the same role. But in 1 dimension, t and x kind of play the same role. And so there's actually a very simple way to prove this, although there are technical problems with doing this. So the idea is to propagate the smallness of ut from a small narrow strip to all of S1. One looks at the wave equation satisfied by ut. So we kind of take the wave maps equation and we differentiate it with respect to time, and we get this this kind of equation that I've displayed here. Special features of this equation are its null structure. So there are these ut squared minus ux squared term and ut times utt minus ux times utx. They have a special algebraic cancellation structure which make these expressions better than sort of generic quadratic expressions. And so then basically to propagate the smallness of ut all over S1, there are two steps one has to use. On the one hand, so I'm going to interpret this equation here as a wave equation with t playing the role of space and x playing the role of time. And so this means I have to have some sort of initial condition, some kind of initial time, which is some initial value of x0, where I have smallness for the data of this wave equation, the data being ut, as well as, well, the derivative of ut with respect to x. And the correct formulation I've written down here, so this involves dt to the -1, never mind. I mean, this is given by a Fourier multiplier on the Fourier side. So we have smallness of these quantities in L2, and we have to show that the smallness gets propagated by this flow of this wave equation here all over S1. And so again, to do this, one uses the null structure here. So these special quadratic expressions, which have special, I mean, in 1+1 dimensions, one sees this special structure by factorizing them, as I do at the bottom here. And for example, if you think of U as a free wave equation in 1+1 dimension, free wave equations, solutions of the free wave equation decouple into a leftward moving and a rightward moving traveling wave. And you see that if you look at ut minus ux, you pick up the rightward traveling wave. If you look at ut plus ux, you pick up the leftward traveling wave. And so it's easy to convince yourself, at least when you use a free wave, that this kind of expression here can be placed into L2 with respect to t and x. And this is kind of the magic null form estimate which you use to propagate the smallness of ut from x0 to any x in S1. Okay, so this is all I want to say about the proof of this lemma, which gives this propagation of smallness of ut. And okay, so then we have to come back to the proof of the proposition, which now reduces to the following. So assuming that this double integral is small, so the other alternative was the double integral is not small. If it's small, well, then I have to be able to pick a time in the interval from 0 to 32 pi, such that the data of u at that time are epsilon close to a geodesic. How does one do this? Well, one uses a simple averaging technique. So first of all, from the lemma, I know that if I have this smallness of this double integral, then I can propagate this smallness actually for ut everywhere. So I know that on any vertical strip, the L2 norm of ut is small. And then one looks at the following quantity, u tilde of x, which is the integral of ut of x times psi t dt. So psi is a bump function, which doesn't matter, it's normalized to size 1, non-negative, and u tilde of x henceforth is a function which only depends on x. And one shows that using this uniform smallness of ut obtained through this lemma, one shows that actually u tilde is an approximate solution of the equation characterizing geodesics. So it satisfies this elliptic equation u tilde xx plus a constant times u tilde equals 0, but only approximately. I can only say that this is much less than 1, where this smallness is dependent on a constant delta, which I have here. But I can say that this smallness holds uniformly for all x in S1. And using this, it's actually not too difficult to show that u tilde actually has to be close to a geodesic. So the constant e of 0, which comes up here, it has to be close to the values 2 pi n squared, where n ranges over the non-negative natural numbers, or the natural numbers including 0. Furthermore, u tilde has to be close to a geodesic at the corresponding level here, energy level. And then one can show, again, going back using the smallness of ut and using the definition of u tilde, that actually there is a time t at which u, the data of u at that time, are close to u tilde, which in turn is close to a geodesic. And this is how one shows that if you have the smallest condition on this double integral, then there is a time where your damped wave maps flow actually has to be close to a geodesic. Okay, so then this is the first. This concludes this proposition. And now the question becomes to prove that theorem that I mentioned at the beginning. Okay, assume that we have now a flow which has arrived close to a geodesic. How can I now push the flow past this geodesic? How can I push its energy below the energy of the geodesic to then continue with the damping stabilization step? And here one has to do something very different. So damping stabilization, of course, doesn't help anymore. Somehow one has to do something which is somehow transverse to this geodesic. And I mean, intuitively, it's kind of clear if you have a sphere SL of dimension larger than 1, and you have some kind of closed curve which is close to an equator there, then of course you can simply push this curve beyond the equator, let's say to the southern half or to the northern half, such that it becomes shorter, and that should somehow decrease the energy of the thing. But of course, to implement this for the controlled wave maps flow is not so obvious, because your control has to be supported on a small set omega, and it's a complicated nonlinear evolution equation, and so it's a priori it's not obvious how you would achieve a decrease of the energy below that of the geodesic. But nonetheless, this can be done. So we have the following proposition: given a geodesic from S1 into SL, there is given a geodesic from S1 to SL, there are constants nu and epsilon small, such that if the data u of 0 are close to the data of the geodesic, then there is a control on omega times 0 2 pi, which is bounded by a constant C0, which is an absolute number, and such that the solution of the corresponding controlled wave maps flow at time 2 pi, so starting at time 0 with my given initial data, at time 2 pi, it has energy which is strictly below the energy of the geodesic. So this is unfortunately not quite correctly written. This should be 2 pi n squared. In general, the energy level of a geodesic is 2 pi times n squared. So this achieves this kind of a decrease of the energy below the energy of the corresponding geodesic. And once we have achieved this, we can then continue with the damping stabilization, as I said before. Now, the idea behind this proposition, this relies on a concept developed by Courant and Crépeau in 2004 in a paper related to the KdV equation, and it's a sort of, again it's a quite nice idea. So the idea is to expand U around gamma in terms of a kind of Taylor expansion, in a power series expansion with respect to some kind of parameter epsilon, a small parameter, and okay, so we then try to plug this into the wave maps, the controlled wave maps equation, where the forcing term is also a multiple of epsilon. So it's epsilon times some function g1 perpendicular to u. And so the question now is somehow, well, can we achieve by picking suitable constants, suitable functions u1, u2, etc., and a suitable forcing term, can we achieve that within a certain time from 0 to 2 pi, we can push the energy of u below that of gamma using this flow? And in fact, so one can do this by formally matching powers of epsilon. So to explain this in the simplest case, assume that the target is S2 in R3, and assume that the geodesic is given by cosine x sine x 0. Well, in this case, one can make a very simple ansatz. One tries u1 to be of the form 0, 0, v, and g1 of the form 0, 0, g, where v and g are functions that are to be specified. And what my goal is to analyze the evolution of the energy with this ansatz up to order epsilon squared, and to treat everything that's epsilon cube and higher as error terms. Okay, so now if one does this matching of powers of epsilon, one finds actually a very simple relation that needs to be satisfied between v and g, which is this Klein-Gordon equation here, box v plus v equals g. And okay, so then one still has to impose initial and final data for V. I mean, this is the kind of linear control problem which I'm solving here. And so for the initial data for V, I choose 0, 0, and for the final data, I choose -1, 0. Okay. All right, so by basic control theory for the linear wave equation, I know that this can be done. I can choose a control function G, which is supported in omega, which achieves this step from time 0 to 2 pi. And if one then plugs the corresponding ansatz with this choice of U1 and G1 into the controlled wave maps flow, one analyzes the evolution of the energy, and one finds the following expression that to leading order, the evolution of the energy at time 2 pi compared to time 0 is given by -2 epsilon squared times the following double integral plus an error, which is cubic in epsilon. Now, okay, so to determine if I have actually lowered the energy of my wave maps below that of the geodesic, I need to understand what this double integral here does. And for that, well, this is actually very easy to do because V solves this forced Klein-Gordon equation here. The important thing is that there is a plus term here in this Klein-Gordon equation, not the minus term. And now for the Klein-Gordon equation, there is a natural associated energy, which is this functional f of t. And its evolution, again, if you look at the evolution of the energy of this functional for this forced Klein-Gordon equation is given by this formula here. And so this double integral on the right here, of course, is exactly the same as the double integral on the right in this expression here. And so in particular, we conclude that the evolution of the energy of the controlled wave maps flow with this choice of forcing is given to leading order by -2 pi epsilon squared up to an error term, which is size epsilon cube. And of course, by choosing epsilon very small, the first term dominates, and I have achieved a decrease of the energy of the wave maps data lower than the energy of the geodesic. Okay, and so this basically completes the second step. And in combination with the first step, with the damping stabilization step, we now see that there is a control which, for arbitrary initial data, reduces the energy to arbitrarily small size. Okay, so this is nice, but there are some other questions you can ask in this context now. So of course, the preceding theorem implies that if you restrict the initial data to energy less than 2 pi, so that the damped wave maps flow can never encounter a geodesic, the minimal energy of a non-trivial geodesic being 2 pi. If the energy of the initial data is less than 2 pi, then the damping stabilization cannot get into this obstacle. And so it's going to converge to something with arbitrarily small energy. And so in particular, you get the conclusion that this complicated control step here in this special case can simply be achieved by means of damping stabilization at first. So you can by just using this a of x times ut term, you can make the energy of u as small as you want at time t, and then once the energy is small, you can achieve the control step by means of standard linear control theory. But then you can ask the question, well, what happens if you have a larger energy level? So if the energy level is at least 2 pi, okay, so we have this somewhat implicit method that I described before, which alternates damping stabilization and the control around geodesics. But you could ask the question, is there a more explicit way to actually achieve this stabilization of my wave map? So is there a function g, some nice function of t, u, and del txu, such that if you look at the forced wave maps flow with this forcing term, that the energy of this actually asymptotically converges to 0, and this uniformly for all initial data of energy at most m. So again, like if your initial energy is less than 2 pi, then this can be achieved by means of just a damping a of x times ut. But the question here is there such a more complicated function potentially, which also works for energy levels which are larger than 2 pi? And okay, so there's of course technical issues with this, because if I just take some arbitrary complicated polynomial function, for example, in TU and del TXU, then this kind of equation that I've written down here, it's not even clear that it's locally well posed in the energy. So this doesn't make much sense. One has to restrict this function G to a much more limited class. And there is a very technical kind of definition we are using here, which is not very satisfying in some sense. Basically, you have to ensure that for this function, when if U is an H1 function, so del TXU are in L2, then G of TU and del TXU is also an L2 function of T and X. So this is something which is certainly the case for the typical damping stabilization function, but in general, it basically means that you have to have some kind of linear dependence on the first derivatives of U, but it could also involve something like sine UT or sine UX, functions like that. And you could have something like a polynomial if you multiply it with a linear expression into del TXU, would also be an admissible candidate for G, for which you have good well-posedness properties of this equation in H1. Okay, so then, so what we would like to achieve is the following. If we look at this kind of forced equation with such a short term, where G has these nice properties that I just described, then if your initial energy is bounded by M, then the corresponding flow uniformly converges to 0 in time in terms of the energy. So you can bound the energy of the corresponding flow at time t by some function h of the energy at time 0 and t, where h is a function which has certain nice properties. It vanishes as t goes to infinity, and it has certain other nice properties. It's increasing with respect to the first variable and so on. So the question is, could we simplify this procedure that I described before by finding a function G of T, U, and del TXU such that this corresponding flow here actually has this uniform asymptotic stabilization property? And the answer is this doesn't work. So if M is larger or equal than 2 pi, there cannot exist such a function such that this force flow that I just displayed is uniformly asymptotically stable. And in fact, this is something, the reason for this theorem is a much more general, is applicable to much more general flows. I mean, this has nothing to do just with the wave flow. You could also have parabolic flows and so on. It's a purely topological reason behind this. But I think my time is up here, and so let me just say, so the reason for this kind of theorem is purely a topological fact, namely linked to the non-triviality of the Lth cohomology group of SL. Okay, so of course you can then ask, so far I've only talked about controllability of wave maps into SL. You can ask, is there also controllability of wave maps from S1 times R into more general targets? And the result is yes, so we can show such a result, but unfortunately it's much less effective. So we cannot make it completely quantitative the way that the theorem that I stated at the beginning can be made. So there's less that we can say in this case. And then of course there's the question of generalizing all of this to higher dimensions, which involves very significant analytical challenges, which I don't have the time to discuss here. Yeah. So thank you, and I stop here.
Thank you for the very interesting talk. It's time now for questions or comments. I want to remember you can ask your questions with the chat, using the chat, or you can raise your hand in the bottom of reactions, in the bottom of your screen.
I have a question for
Yes,
Professor
go ahead.
Krieger. Yes, Professor Krieger, thank you for your talk. My question is the Z omega. Your talk during your talk, you say that was an open subset, right? Open subset.
Yes, I mean you can take any any interval, any open interval, sure. Yeah.
The question is if one can, because you know in control also there are some problems in which one take the Z omega to be measurable set, some measurable set. So just to ask if you know something about.
Yeah, that's a very good question. So actually, so in the technique that we use, so remember, like there is this damping stabilization step. So the damping stabilization step involves the function a of x times times ut, and so there it is. In the beginning, there's this proposition which I say, which gives this dichotomy. Either this double integral that is played is larger than delta 1, or you can extract a time for which you're close to geodesic, and this in turn relies on this this continuation, this approximate unique continuation property. And to prove this approximate unique continuation property, you so you look at the wave equation satisfied by ut. And for this wave equation, I said you have to have the right initial data. So you have to sort of pick an x0 for which the initial data for this wave equation for ut are good. And this involves certain averaging procedures. And so in particular, you have to, I mean, for the data for the wave equation for ut, there's ut itself, but there's also this utx quantity. And to get smallness of the L2 norm of that, you have to use another averaging argument, and you have to use integration by parts tricks, and this involves derivatives also of the function a of x. So somehow, like this method that we are using, it seems to require somehow that you really have a non-trivial interior of your set. But it's a very interesting question. I don't know, like the techniques that we're using would break down, I think, if omega was just measurable, at least in terms of the effectivity of what we're doing and so on. So I'm not sure if this could be done.
Okay, we have a comment in the chat. Adrian Franco says, best regards, could you put the slide or talk about some reference or the bibliography about the talk, about this topic, please?
Yeah, sure. I mean, again, so I don't, I was somewhat surprised. I mean, it seems like this question really hasn't been investigated very much yet for these kind of equations. And so I should say, I mean, I didn't have the time, but if you go to the higher dimensional case, so you don't look at S1 times R, but let's say you look at wave maps from S2 times R into S2 or something, then it gets much more interesting, because then you have bubbling phenomena. So then even the undamped or whatever wave maps flow is going to have finite time singularities. The analysis of these singularities has been achieved only recently. And so if you want to actually prove a controllability result in that setting, you would have to, that's my opinion, you would have to sort of understand, first of all, this singularity structure results like Deukat's Koenig-Mell and so on have done for the damped wave maps flow, where you probably have analogs. And then you would have to sort of use a control step which is also close to singular solution. So let's say you don't converge to like a nice geodesic, but let's say you converge to some kind of multi-bubble kind of solution. And then you have to use control to kind of avoid this singularity phenomenon. And this is a bit similar to, maybe it's a bit like some of these geometric flows where one uses surgery. So one interrupts, if a singularity forms, you interrupt, you use surgery, and you continue. And here you would use control close to singularity to avoid that. So I think there are very interesting questions in this, and which would give also reason to further understand these kind of singularity, classifications a la Deukat's Koenig-Mell, but with the purpose of doing something which is maybe completely practical, right? Like this kind of controllability for these kind of equations may have engineering applications after all. So I think this is yeah. But yes, maybe you can write me an email, and I can send you references. But really, there isn't that much on this kind of equation. And I mean, I should also say there are all the other analogs, like the for example, the parabolic analogs, harmonic map heat flow, which you could also try to control, but of course that's more difficult because it's parabolic. You can't flip the time around and so on. So, but I think there are many interesting questions that can be asked here in this context.
Okay, Professor, thank you. Any more questions? If not, then let's say thanks again, Professor Krieger.
Well, thank you very much.
Okay, I just want to say some things before. We got another questions.
Yeah.
In the chat, Alejandro Chiari, has there been any work done on those analogs you mentioned?
Not as okay. So I mentioned these references with really these very explicit applications, and there was a paper recently on Landau, Lifshitz, Gilbert. So it's a generalization of Schrödinger maps, but this is again it's not the kind of setting that I'm considering here. So this is more like local control, kind of close to using kind of linear theory especially. It's not this kind of totally global viewpoint that we have. And I mean, part of the reason is, of course, because even, for the Schrödinger maps, our understanding is much poorer than for wave maps in terms of the solitone resolution and even global well-posedness in very nice settings. So that may be a reason why, but no, I mean, like, especially, for example, there's also this half-wave maps equation, which I mentioned before. I mean, there the difficulty is you don't have the finite propagation speed anymore. And so you cannot use this kind of nice Huygens principle that we use many times in this work here, finite propagation speed. But I think there the question is also extremely interesting because there are many non-trivial steady states in the one plus one dimensional setting, and the question would be how to mix again a damping step and then a step around these steady states to get controllability. And again, it might be of physical interest for the half-wave maps. So this would be kind of something that I think would be interesting to look at.
Okay, Professor, thank you. Well, like this, we conclude this third day of conferences. I want to thank all the audience for the attendance. We have a good attendance. And I want to suggest you visit our website. I'm leaving here in the chat to get more information about this initiative and future events. And I don't know if you want to say something else.
Thank you, Brian. Maybe to say something about to share some information about the structure of the conference tomorrow and after tomorrow. So I would like to say thanks to all the participants for joining us in this third day of the conference. Today we had amazing talks by Professor Kolding from the Massachusetts Institute of Technology, by Professor Enrique Fernández Cara from the Universidad de Sevilla, by Professor Jenny Fragnelli from the University of Stuscia, and our last talk by Professor Joaquin Krieger from EPFL. So this was somehow a mixture between tools of differential geometry, control theory, numerical analysis, harmonic analysis, that showed during this talk that the relevance that these days has the area of partial differential equations, and also the interdisciplinarity of these techniques. So I would like to invite you to the talks of tomorrow, Friday, by Professor Felipe Linares from IMPA, Professor Bojan Siracon from PUC Rio. Also remember, tomorrow we only have the 2 talks, and our conference finish on Saturday with the session of Professor Enrique Suazua. So thank you to Professor Juan Limaco, to Diego Sousa, and especially the organizer, Brian Grajales, who is a researcher at the Universidad de Campinas, from where he is in charge of the streaming of the conference in YouTube. So thank you very much, and see you tomorrow.
Bye. Bye.
Bye-bye.
Thank you very much. See you tomorrow.
See you tomorrow.